knows? Okay. If you, okay, if you think you will be moving, I will leave it like that. Which file? Oh yeah, it's a little bit. LightOn. It's perfect. Okay. So I think Igor will start with like a 5 minutes just presentation, and then it's your show for the time of your presentation. Oh yeah. Sorry, of course. To decide to come on? So we will be starting very shortly, in like 5 minutes. We are slightly late, I'm sorry. If you want to grab a coffee or any something quick to eat just outside, feel free to before we get started. And we will have a 3 presentations to start with, and then a coffee break at around 4, I think. Depends on how on schedule we are with the presentations.
Alors j'ai mis live en fait.
D'accord.
Ça marche?
Je peux check si tu veux.
Ouais.
Ouais, on est bon.
Ok.
On est bon.
Ouais.
Should I give you my files right
Oh
now?
yeah, sure. Yeah, you can do it right now, so we can.
Yeah,
it would be
let's
easier.
make sure.
That's a very good idea.
Okay.
So you are next after.
Right.
After Ada.
So the file is called presentation.
That's quite easy. Presentation, really cool, blah blah blah.
Yeah.
Okay. Where is this song coming from?
Yeah.
Oh. My bad. Okay. I'm putting your file, yes. Already got it. That's so good. And let me give you back your USB key. If it decides to come off.
I don't care. You can
Yeah.
listen to it.
No, all good.
Yeah.
Let's go.
Hello everyone. My name is Igor Kern. I'm the CEO at LightOn. We're very glad to have you over here today for a small workshop on areas, ideas that are of interest to LightOn and the general community, research community at large, on random projections, random matrices, and everything around them. Really try to present to you. So Julien Launay is basically a base a PhD student. He's been very helpful in making this a reality, especially the whole streaming. So thank you, Julien, for helping us out on this. So we're going to have several talks today. The first one comes from Birmingham with Dr. Caban. And then we'll be having a discussion with Bogdan from up south. And eventually we'll have Gavin, who's going to be giving a presentation from Toronto, right? And then we'll be having people from LAR on physics and the use of the OPU. They are not here right now. Yeah?
No, those are already here.
Oh, all right. And then eventually we'll be having a second remote presentation because of the strikes from Mathieu back in University of Opal or whatever. Anyway, so thank you for coming. One of the reasons we are interested in talking to the research community, LightOn is basically a smallish startup. We've been getting funding twice already, and we hope to continue a bit further on. We are designing optical coprocessors for artificial intelligence. And basically right now we're in the 20-ish numbers in terms of people working with us. The next big thing at LightOn is going to be the ability for the research community at large to be able to use our optical processing units on our cloud by Q1 2020. And we hope that some of you, aside from the beta users that are already here, are going to be able to use this as efficiently as possible and help us in growing this area of the hardware community. So without further ado, we'll start with Dr. Caban. Where are you? Okay. And so, thank you.
Let me get presentation ready. Okay. If you want a microphone, it's as you want. If you prefer to talk or to just without or with, it's as you want.
Let's try it without, but have it.
I mean, yeah, give it close by and.
If it's got to talk on the.
Yeah. So.
Is it better with or without?
I think you have to.
It's not on. Let's see what. Is it better?
Yeah.
Put this on just to see the time. Okay, so I'm going to talk about some work that we have been doing in Birmingham with random projection used in machine learning.
Can you put the microphone closer to your mouth?
All right. So one of the motivations of this work is high dimensionality and increasing dimensionality of data. And as we all know, random projection is computationally attractive, even with the traditional computers. The questions we are addressing is, what is the effect of doing this random projection? So with reduced dimension with random projection, what can we expect and what can we guarantee from a subsequent learning machine, like a classifier or a regression or other learning machines? And in particular, what are the conditions under which random projection will not lose too much of the accuracy of learning? So I will introduce the concept of compressive learning that is not new at all, but there are some new developments there. And then I will talk about a generative model called facial discriminant analysis, and what guarantees are there for this method if we pre-process the data by random projections. then I will try to present a generalization of the findings and see how in the PEC learning framework, where we don't assume anything about the distribution, what can we say then? And if time permits, then I will also outline gains that are achievable by combining several random projection classifiers. But mainly I want to cover the first 3 points. So mostly, so we have had a series of papers on these topics, but mostly in these papers is the content that I'm going to talk about. So a famous result in this area is the Johnson-Lindner-Strauss lemma. I think we are all familiar with this. So you fix an epsilon tolerance, and if you have a set of n points, where n is a finite integer, then you need to set the target dimension k of order logarithmic in the number of points divided by epsilon squared in order to guarantee that there is a linear transformation of the high dimensional data that preserves the square Euclidean distances up to a tolerance of 1 plus or minus epsilon. So this result is from 84, and later on in 2002, Dasgupta and Gupta gave elementary proof of the same result, basically just using a Chernow bound and union bound to prove that a Gaussian random matrix does this job with high probability. It is also known by now that this random projection is optimal amongst the linear dimensionality reduction methods, in the sense that there exists, for any n sample size, there exists a set of points which requires this target dimensionality. So that means that if we don't assume anything further, then the k of order log n over epsilon squared is required. We can't get away unless we assume more. And the interesting thing is, what can we assume and what is a realistic thing to assume on machine learning so that we can get better. From this result migrated to machine learning in '99, where seminal work by Arriaga and Vempala, where Arriaga is a psychologist, Vempala is a mathematician, and they used random projections. So this is pre-compressed learning. It wasn't called compressed learning because it's before compressed sensing. So they came up with the idea that we can learn a linear perceptron from randomly projected data, and they put this forward as a new theory of cognition, basically, of how learning happens. One of the key things to notice here is that the guarantee or the target dimension, neither of them depend on the original dimension. So basically, their idea was, maybe in our brains, this is how information gets processed so efficiently. It doesn't matter what is the ambient dimension, only matters some information content, which is, in this case, just quantified by the log number of points. Second source of, so this was in '99, but then 10 years later, Maillard and Munoz came up with a quite similar strategy for regression. A second source of ideas, similar ideas, is when compressed sensing made a lot of progress, and the restricted isometry property looks quite similar to the Johnson-Lindner-Strauss property that we have seen before. So here we define that a matrix R has the restricted isometry property if the square norms get preserved up to 1 plus or minus delta, where delta is a small number. But this time we define it for vectors x that have a sparse representation. The reason for that is that the goal in compressed sensing was not primarily to preserve distances, but to recover the original data x from random measurements. And so the formulation is slightly different, but actually the idea is quite similar. And one key difference is that now the target dimension k is not of order log number of points, but it's of order log of s, where s is the number of non-zeros in the vector x. So the sparser the vector, the easier it is to recover it. In other words, the more you can compress it and still recover it. Okay, so this is a major progress in the sense that in the Johnson-Lindbergh-Strauss result, the structure of the underlying support of the data, or the structure of the set to be projected, was not taken into account. So we needed to have a finite set of n points. Whereas here we can have an infinite set. You can have infinitely many points, but as long as they have a sparse representation with no more than s non-zeros. So when this result was obtained in signal processing, then machine learning has came up with the idea, with the concept of compressed learning. So from compressed sensing, compressed learning has been defined as learning from randomly projected data that has a sparse representation. Now this sparse representation was very important in compressed sensing because they wanted to recover the signal. But in machine learning, it's just a convenient means of inheriting an assumption which then assures us that we will not lose any information from the data, since we can recover it anyway, so we can do learning on it. Two example works, not by any means the only ones. Goldenberg showed that supervector machine can work very well if the data has a sparse representation and it from randomly projected versions of the data. Similarly, ordinary least squares regression also has a good guarantee if the data has a sparse representation. So our questions have been, is this sparse representation anything that is required in machine learning, given that we are not necessarily in need to recover the original data? All we want to do is to do good generalization. So maybe that is an easier problem and we can get away with less or with different conditions. That's kind of interesting question. A related question is, do we really need to preserve all the distances uniformly, like those two results that I reviewed here? They all guarantee that all pairwise distances are preserved approximately. So do we need all of them? Since in machine learning, sometimes some points on some distances are more important than others. And if not, what are the structural characteristics that matter in this context? And finally, whether we can draw further gains by combining several learners that each have a randomly projected version of the data. So in order to pursue answers, or partial answers at least, to these questions, first we can look at this very simple classifier. So this is called Fisher discriminant analysis. You have two classes, and it's assumed that both classes are Gaussian distributed, and they have the same shape of covariance, like on the picture. So any new point, test point, that needs to be classified is going to go to the class with the smallest Mahalanobis distance, where the Mahalanobis distance means that the metric is the one defined by the covariance. of course, it's a simplifying assumption. In reality, the true covariances may not be the same, but and the data might not be Gaussian, but this is the model. So part of our analysis is that it can be a misspecification. This is what the decision rule looks like associated to that model. So x is the query point, and then mu0, mu1 are the two class means, and the sigma hat is the estimated pooled covariance, R is the random projection. So if we were to randomly project the data, do Fisher discriminant analysis, this is how the predictions are made. We want to know how good are these predictions. So what is the generalization error? The classifier is denoted here H hat superscript R, and X, Y are the query points. Of course, we don't know the Y, we only observe the X. We want to know what's the probability that the prediction will be wrong. So we took a different approach from compressed sensing based compressed learning. We are not assuming that the data has sparse representation. We want to know what is needed. What do we need to assume in order to guarantee that there is not much mistakes made by this classifier? So we start from the generalization error of the classifier. So first we fix the training set, we fix the random projection matrix instance R, and in that case we can have the exact form of this probability of error, because X is, remember we assume the classes are Gaussian distributed, so X has Gaussian distribution, and if we fix everything else, then this whole left-hand side is Gaussian distributed. We can work out its mean covariance, and so from the CDF we have the first line there, the error probability. And then manipulating that, massaging it into 3 different terms, then we can distinguish what are the important characteristics that we need to take care of to be preserved. So the AI is the distance between the mean estimates in the metric defined by the true covariance of the class. The BI is a term that captures the covariance misestimation as well as the covariance misspecification. So the sigma I in the middle is true covariance for the I's class. The sigma hat is the estimated covariance, which is a pooled covariance from the model, and K, kappa, is the condition number. So the smaller the condition number, the better we are doing. But it's nice to see the exact expression that this is what it depends on. And the CI is the misestimation of the means. So we have these 3 components of the error. So in order to see what happens with these 3 terms, then we have to develop some tools. And in particular, the interesting part was here to bound the largest and the smallest eigenvalue of the projected covariance. So given a sigma matrix and we project it by the random projection into a smaller dimensional space, then what can we say? What happens to the eigenvalue, the extreme eigenvalues? We will be using the notation R sigma to denote the so-called effective rank or effective dimension, which is the trace of this matrix sigma divided by the largest eigenvalue. So this is what we got, given the sigma covariance matrix D by D, so it's a large covariance matrix and it can be singular. Then with probability 1 minus x of minus epsilon square over 2, then we have an upper bound on the largest eigenvalue of the projected covariance, which depends on the trace of the sigma, and the largest eigenvalue of the largest eigenvalue. And this plus here means that we have to truncate if that expression goes negative. So there is, of course, another way, an easy way to do the same. which turns out to be not as good because so this matrix that we are considering is weighted Wishart, this R sigma R transpose. Whereas in the literature there has been a result for the Wishart without the weighting. So we could, in principle, we could take out the lambda min and the lambda max, and apply the result for the Wishart, and we would get an expression that depends on the dimension of the matrix with D, and there is no way to get around that. Whereas in this case there is no D anywhere, so this is dimension free. In terms of tightness, we see that the expression that we have here, the trace divided by lambda max, is always no larger than the D that we have here. So the upper bound is better. The lower bound can be better or worse. We can't say anything definite. However, here is an example. So upper bound on the left, lower bound on the right, where we see the actual empirical values. These are these blue ones. So we generated the matrix and projected it several times, and each time we plotted what are the largest eigenvalues, and here what are the smallest eigenvalues. And the black one is the bound that we would get if we just apply the existing method, and the red is what we got from our bound. So that looks quite nice. I already said this. And then we go back to our problem and plug it back and work out. So there was those three terms, and this is the generalization error then for the Fisher discriminant analysis. It looks quite complicated, but actually what matters here is that we can pick up what are the characteristics of the problem that make this bound smaller. So the difference between the means, the smaller that is, the larger the error it is. So the more far apart are the means relative to the lambda max, the easier the problem. And there are these terms that go away when n increases, and then there is this g, which is a decreasing function of the condition of a condition number, and that's a condition number of a matrix that encodes the misspecification of the covariance. So remember, we assume the pooled covariance, but actually the true covariances can be different. So it looks complicated, and I don't want to spend too much time on it. That's the matrix that is Mi that encodes the misspecification of the covariance, and that the condition number of that number, that matrix, is this one here that goes there. So it captures the effects that matter. A little bit cleaner. If we take n to infinity, then some of the terms will vanish, and we can pick out more clearly that the distance between the classes and the covariance misspecification have the most effect in the bound. But now it's interesting to look, so what's the random projection effect on these? And it's not too difficult to see from the analytical expressions, but it's also nice to see experimentally that as one would expect, in fact, that the distance between the means gets worse if we project it to lower dimensions. But what is more interesting is that the covariance misestimation and misspecification gets better if we project it. And if you think about it, it might look surprising, but if you think about it, you have very elongated covariance, so high condition number. After projection, chances are that it will be better conditioned. It's a smaller matrix anyway. And the third term also comes out better. So if we project more, then we can estimate better because we don't have to estimate a d-dimensional mean, we only need to estimate a k-dimensional mean. So to sum up, the distance between the classes gets worse if we compress it more, but the other things get better. And putting them, the three terms together, give the overall bound. So the red is the upper bound, and the blue is the observed performance. And there is a sweet spot there where that k is the best choice. Now that was synthetic data, where we generated the data ourselves, so we knew what we wanted to expect. So in that generated case, the covariances had the first few so we generated the diagonal matrix first. The first few elements were set to 1, and then the rest was set to decay as 1 over I squared, where I is indexed to those diagonal elements, and then we randomly rotated it and for one class, and again randomly rotated it for the other class. So that's how we generated the data. But now it's interesting to see what happens in real data. So one context where similar characteristics can be observed is when we go from low-dimensional, non-linearly separable data up to high dimensions, like kernel machines are doing. Because the kernel transformation is a smooth transformation, therefore we can expect that after this high-dimensional transformation, the space will not be totally filled, so there will be a covariance whose trace is quite small. So remember, in the bound, there was a trace of the covariance. So if the eigen spectrum of the covariance decays fast, then we can expect to do better. In other words, if there is a small intrinsic dimension, but not necessarily in the sense that everything fits on a subspace, but it decays fast, then we can do better. So we expect that that happens with the kernel transformation. And also the kernel transformation hopefully makes the classes more distinct, the means more separated. And indeed we see that if we run the classifier on the full kernel, we get this red line. If we instead use random projection, then we get something very similar. So unless we compress too much, where too much can mean something like 10 or less, then we do almost as good or even as good, or even sometimes slightly better. But we can't really, we don't really claim that it's significantly better, but no worse is good enough. And this happens quite early on. This is on a number of data sets, 13 data sets we tested it. Here, a little bit more. Okay, it needs to be little bit larger, but not by too much. So to sum up this part, there was no spatial representation requirement anywhere. So we didn't start from the assumption, but we derived what is needed from what we want to achieve. And as a result, we can say that random projection has a beneficial effect on the misestimation and misspecification of covariances. It has also a beneficial effect on the misestimation of class means, and the bad effect on the class separability. And all the assumptions we needed for this was that the trace of the covariance is finite. So we can even have D to go to infinity as long as the covariances are trace class. All right. Now we want to see how much of this can be generalized. So far we assume that the classes are Gaussian distributed, very strong and simplifying assumptions. However, as it turns out, that the analysis itself was quite complicated. Now we want to say something more general. The analysis is going to be simpler, but of course the details are not that much there. So when we want to do more general claims, then of course the claims will be not as detailed as they were in the analysis that I presented for Fisher discriminant. So now we are in a distribution-free setting. We're not assuming anything about the distribution. We have an input domain, XD, d-dimensional input domain in the d-dimensional Euclidean space. We have the targets, which for classification they are -1, 1. We have a hypothesis class, which means a set of functions from where the machine learning algorithm picks one based on the training data. We have a loss function, we assume that it's bounded. That's for convenience, and indeed that would be quite difficult to relax. Training set, what we really want is the classifier that minimizes the generalization error. But as we all know, we can't get it because we don't know the distribution of. So the same approach that worked for Fisher discriminant, now we have to find something different. To make the notation easy, then we are going to denote functions of this form. So this is the classifier output, the true label, the loss. So all this will be denoted by G with inputs X and Y, or we don't even write the inputs, we just write G, like here, and like here. So when I write this, I mean generalization error. So that will make the subsequent slides a bit cleaner. But now I want to do this on the compressed data. So we take the random projection matrix as before, K by D, K smaller than D. We compress the input domain. We consider the function class that takes K-dimensional inputs. We compress the training sets inputs. We leave the targets as they were. And we use similar shorthand where GR is going to be a K-dimensional function from the compressed class. And we are particularly interested in this algorithm. So the algorithm will find the function that minimizes the empirical error. We do that all the time in practice, but if we do it in the high-dimensional space, then there are problems, which I'm not going to talk here, but they are in textbooks as well. And we want to know what's the generalization error of this one. So all we do in practice is we project the data, we minimize empirical risk, and the classifier that we get that way, then we want to know what's the generalization error of that classifier. And we want to know it relative to the best one in the original class. The bound is going to use this notion that we call a compressive distortion of a function. So that measures, now this is with the shorthand, so basically we measure the loss given a function g, which will be in our case the empirical risk minimizer. So given a function, we look at the loss of that function on the original space and in the compressed space. We take the difference, take the absolute value of the difference, and we call that the compressive distortion of the function. It's always non-negative, it's bounded as long as the loss is bounded, and if k is large enough, then it's going to be 0. In the worst case, if we take k equal to d, then it certainly is going to be 0. But what's interesting is when the compressive distortion is small, not necessarily 0, but small, when k is much smaller than d. That's the interesting part. And we see from here why. So this is a generic bound on the empirical risk minimizer in the compressed space, because the generalization error is bounded from the error of the best classifier in the original class, plus this distortion that I talked about, the compressive distortion of the best classifier in the original class, plus the Rademacher complexity of the compressive class, which is usually smaller than what it would be for the original class. It's a more restricted class of functions, plus some deviation term here, which is small, goes to 0 as the distortion goes to 0, and plus the usual distortion, this last term that used to be in generalization bounds, in classical bounds as well. So this R hat is the so-called empirical Rademacher complexity. It's a measure of complexity of a set or a function class in the classical theory. So if we were not doing random projection, then we would have here the empirical minimizer of the origin, so the high dimensional space. We would have the first term on the right the same, the second term would not be there, the third term would be the Rademacher complexity of the original function class, which is larger, and then we wouldn't have this term, and we would have the last term. And as I say, the interesting thing is when the compressive distortion is small, because if it's small, then the second term is just that small number, and this term is just that small number. So the next question is, when is that going to be small? And that's where the analogy to compressed sensing is. So if the data has partial representation, then we can expect that this one is small. But it's not as straightforward. Maybe there are other things that would make that small, for learning in particular. So we went through a number of examples where from simple to complex. So first is just hard-based learning, linear separation of classes, then generalized linear, then multi-layer perceptron, nearest neighbor, which is unconstrained, and more generally Lipschitz classifiers. So what we found is, so we work out what's the compressive distortion in that model, and what's the Rademacher complexity. But this second one, there is nothing new about it. And it's expected that if the Rademacher complexity was dependent on the dimension, then D goes down to K. That's why we are doing it. But what happens to that term? So for the half-space learning, we found that the compressive distortion can be bounded by the moment generating function of the distribution of margins. So each point has a margin, which is the distance to the separation line or separation hyperplane, and the moment generating function of that distribution is what makes the distortion small. A picture that explains why that is. How much time I have?
10 minutes more.
Okay, good. So, yes, so generalized linear model. So now we move from hard-space learning to linear learning with the Lipschitz laws. And then this is quite a crude bound. Actually, there is a more detailed bound, but we can see the main characteristics anyway. So it works out that an upper bound is the true norm of the classifier times some constant terms that don't depend on the parameters of the classifier. Namely, is the expected norm of the data, which can be written also as, can be upper bounded as the square root of the trace of the XX transpose. So that tells us that if the eigenspectrum of XX transpose decays fast, then it's going to be small. And of course the term decreases when K increases. So it tells us that we can reduce the function class complexity from square root of D to square root of K, provided that it's worth it, namely that this distortion term is small. So when is it small? When this is small, i.e. when the margin is large. So it tells us things that we already knew, but it's nice to find them from this random projection distortion principle. Quite similar result for multi-layer perceptron. This is a two-layer perceptron, the classical one, with sigmoidal activations and Lipschitz laws. So quite similar to the previous, except that now we also have the Frobenius norm of the first layer weights. So here we took one norm regularization on the upper layer, and that was for convenience. It's easy to derive the bound that way. And no regularization on the lower, on the input layer, and that's because we expected that the random projection has a regularization effect, so there was no point to put an extra regularization. And the whole philosophy of this is that we don't put constraints without a good reason. So we assume we don't know anything beforehand. A random projection tells us what would help. And it tells us that it would help to have those norms small. All right, some experiments and this data. I know it's a toy problem, but it was the first exercise for my PhD student. And we see the original classifier, multilayer perceptron is the flat plane, and the orange is the randomly projected one. And as k increases, the accuracy increases quite sharply. And this is the computation gain on personal computer. Next example is nearest neighbor. So this is not a classical nearest neighbor because the classical one is not base consistent. This is a version invented by Kontorovich and Weiss, and it can be interpreted as an empirical risk minimizer. So basically what it does is it writes the decision rule as a Lipschitz function. So it's this H here, where n minus x means the nearest neighbor of x in the negative class. X plus x means nearest neighbor of x in the positive class. And if we take the difference of the distances from x to those two, and we minus them and divide by 2, we look at the sign of this quantity that's actually taking the nearest neighbor. But then, if we put this into a Lipschitz loss function, and we minimize that, with a special loss actually, it's a ramp loss, like the hinge loss, but clipped at 1. Then that actually does, will exclude some of the points that don't fit in the margin defined by the ramp loss function, and can be interpreted as an empirical risk minimizer. So we can use the same bound and the same framework. However, the original one would have a bound of this order, which implies sample complexity of exponential in D. So you need exponential in D number of training points in order to do well. So we want to know, does random projection tell us a condition when you don't need that many? So we'll work out the distortion, and that should be, the GD shouldn't be there, it's typed. And it's upper bounded by constant times the Gaussian width of the support of the distribution. So this W XD is the Gaussian width, is the same quantity that is used in learning theory as Gaussian complexity, but here it's applied on the support set of the inputs rather than the function class. And so it's a measure of intrinsic dimension of the data. With this, then we get sample complexity exponential in K only, where K has to be the square of the Gaussian width. So in other words, instead of exponential in D, we only need exponential in the intrinsic dimension. This generalizes to Lipschitz classifiers. So I told you in the previous slide that the classifier was constructed to be a Lipschitz function. Now, does it have to be nearest neighbor? No. For any Lipschitz function, we can get the same bound. So Kontorovich studied these classifiers in detail. And we get basically the same flavor of results, except that he looked at it in metric spaces, and the intrinsic dimension in that context corresponds to square of Gaussian width in our context. So it's different interpretation. We can also generalize a little bit. So in the previous example, we needed to have the support of the inputs a bounded set. Actually, that's not needed as long as there is a subset of that contains 1 minus epsilon of the measure. That's good enough. And then the distortion works out to be bounded with this quantity where if the support was a compact set, then this would be 0, this would go, we get back what we had, but if it's not a compact set, then we have an additional term which is a small term. And this indeed is the case. So much of the criticism for learning theory used to be that, okay, you have some guarantees on paper, but they don't correspond to what happens in practice. This one does seem to correspond. So if you have data that lies on some structures, simple structures, then the sample complexity, so we plotted the error, observe the test error as the sample size grows, then indeed we can observe that whether we work in the original space or the compressive space, simpler structures allow us to learn well with less points. It also works when the structure is not a linear structure, so we tried this Swiss roll. We tried sparse representation data, so yes, it works, but there is a lot more to it, so sparse representation. On this axis, the sparsity means the number of non-zeros in the data vectors. On this axis, the n is the sample size, and on the z-axis is the test error, and we see that it makes a big difference. If there is a sparse representation, then the error goes down much quicker. If the data is on a subspace, then we see this structure, even if we work in original space or the compressive space. So, summing up this part, the compressive distortion quantity that we define captures the structure needed for being able to solve a hard dimensional problem in low dimensional random subspace. And there was no sparse representation required. If sparse representation is present, it can help in nearest neighbor case or in the Lipschitz classifier case. But otherwise, the range of helpful structures is quite large. I know my time is up, so I just want to mention that an additional thread of this work is to combine several classifiers, each having its own random projection, into an ensemble, and we can we try this on Fisher discriminant analysis, and we see something like this. So on the original space, in the original space, we have this blue line, and all the other lines are random projections. So the green one is a single one, then 10 random projection, 100, and 1,000. And these are gene expression data, so the kind of data this is most suited for is when you have high dimensions, low sample size. That's when the improvement is the most noticeable.
So thank you, Atta, for this talk. We have time for a few questions, maybe. We do have a coffee time afterward if you want to ask questions directly as well. But if you have a question now, we have time for one or two questions now. Yeah.
I know already it was very complicated, so I didn't get what you mean by ensemble of random projection. That means you take multiple random matrices,
Yes.
you do the projection, then you average. And doing this works better in what case? I didn't
Yes. So say we have an ensemble of 10 classifiers, then you generate 10 different random projections independent of each other. You project the data through all of them. So and each classifier receives one version, one random projection version of the data, and outputs some prediction. And then you have to come up with a way to combine them. It can be done in several ways. Majority voting is quite popular, but it's harder to analyze. The other, the scheme we analyzed was that we took the linear output and averaged it. And then for the Fisher discriminant analysis, we were able to derive the generalization bound. But nowadays we are extending it for other classifiers.
One more question, maybe?
Thank you for the talk. What's the intuition behind the fact that random projection acts as regularizer? Like, what's the intuition behind it?
Okay, so one intuition when you're working with a single random projection is that the function class gets restricted. So instead of having to learn in the linear classifier case, instead of learning a vector of d dimensions, you only learn a vector of k dimension. This restriction is already a regularizer. If you have a complex model and you only randomly project the data, then it will be less of a regularization effect. It will only affect in a neural network the first layer. But you can, nothing stops you to extend the idea and do random projection in each layer, then it will look a little bit like dropout. In the ensemble case, the regularization effect is a joint effect of combining several of these that I mentioned, and so the variability gets reduced. So conceptually similar effect, but less variable result.
So if we try to learn the neural network on randomly projected data, what you're saying is that we wouldn't have this regularizing effect?
On the first layer, yes. So then you don't have to regularize the first layer weights.
But the rest still requires regularization.
Yes, so we didn't try not to regularize the rest, mainly because we were not able to derive a bound in that case, which is already an indication that there is no simple guarantee for that case. So you still need the regularizer. The random projection provides such an effect, but it only provides where you use it. So unless you use it in all layers, then you still have to find another way to regularize, basically.
So we'll have more time once again at the break if you have a question, or if you think of a question on the way. Next up is Bogdan. Good job, So next up is Bogdan, who's going to talk to us about medical applications for. Oh, you have.
Laser pointer.
Oh, laser pointer. Yeah, that's. Okay. That's the results.
Okay.
Yeah,
it's
no,
fine.
it as a keyboard, but. And let me get your presentation. Sorry. Whoop. And okay. Put it here. Okay. Okay, perfect. Do you think you will be staying on here or? Yeah, just for the camera.
I will be moving.
Okay, I will adjust it. Perfect. So yes, Bogdan will be talking about medical applications of low precision neuromorphic system, and I will let him go.
Good afternoon, everyone. My name is Bogdan Penkowski, and I work at the University of Paris-Saclay. So today we are going to talk about low precision neuromorphic systems and their medical application. And as you can see already from this slide, the purpose why we use these neuromorphic systems is to get energy efficient data processing. So this work is done in collaboration between Seduzen Institute of Technology in Delhi, Aix-Marseille University, and the LITI in Grenoble. Okay, it works. So, yeah, let me give some background, some motivation why we may need to use smart diagnosis devices. And in fact, it is apparent that there are many use cases where one can benefit from artificial intelligence or machine learning, for instance, at home. So this is important, for instance, for prevention of different medical conditions such as strokes, epileptic seizures, and heart attacks. Moreover, even if such event happened, smart diagnostic is useful for rehabilitation and post-hospital monitoring at home. Finally, there exists a class of so-called brain-computer interfaces which allow someone to input information using just their thought. So typical or canonical case is someone who is on a wheelchair and they use the brain communication with the computer to move this wheelchair, right? Or to type some text on the screen and so on. These brain-computer interfaces, they can be useful also to monitor workers or drivers' fatigue, so that to prevent accidents. Also, to the same about pilots, sport athlete monitoring, to monitor performance of football players, for instance. And also, it gives more opportunities for gaming and VR. So what are current challenges of this kind of devices? Well, now everyone can use Siri or Google Assistant service or Amazon Alexa, but all of them at the moment they send all the data to the cloud, to the data center to process those data, and this is quite problematic. So not only this requires more energy, but also we have privacy and security concerns. So maybe someone of you didn't know, but actually Google hires people to transcribe sometimes what you have told. And for case of your medical data, this kind of risk is completely unacceptable. Finally, what if someone is in airplane where there is no internet signal or if internet is temporarily not available? Then they cannot use the brain-to-computer interface or other device. So the viable solution to this problem is to go on the edge. By the edge, I mean working on a mobile device, whether it's a smartwatch or some other wearable accessory. And in that case, indeed, these devices can work everywhere where there is no internet, and also they would increase mobility, but that requires battery power. Therefore, there exist different constraints which smart diagnostic devices have to adhere to. So those are size, weight, and also amount of on-chip memory. So why are we interested actually in this, in the last one, on-chip memory? So recently it became evident that the most of energy wasted by a computing device is actually wasted for data shuffling between a processing unit and a memory. So you can imagine this the following way. You are having a restaurant, but the food that you have to cook is outside of Paris. So you have to take a car to drive somewhere and come back. So that's what's happening in our devices when we access external memory. So the goal in this case is to put processing close to memory as much as possible in order to reduce energy expenditure. Okay, so we need an algorithm which inherently supports this in-memory computing. And one of those algorithms are actually artificial neural networks. And in order to maximize the benefit of artificial neural network, we go to binary. So in this case, a neural network will have binary synapses, okay? And also it will have binary weights. So that instead of using classical multiplication circuits, if you are designing hardware, you replace those operations with simple XOR. So in our work, we design resistive RAM blocks as this kind of binary synapses. So let me just summarize what I mentioned in the case of a neuron in artificial neural networks. So first, you have dot product computation, right? So first you have multiplication, and then you have summation. Finally, you use some kind of activation, which can be rectifier linear unit or some other function. When one works with binarized neural networks, the role of multiplier is a simple XNOR gate. And the summation is replaced with a bit count. So you can imagine that this substantially will reduce the area. Finally, activation is a simple sign function. So here is the comparison, what we achieve when we go to binarized neural networks. So first, instead of using 32-bit numbers, we just use 1 bit, and therefore the memory reduction can go up to 32 times. In practice, it's less, since you may need more neurons in actual binarized neural network, but still you gain some memory. Then instead of using sum, you just count bits and use very simple activation. So this, of course, this benefits in terms of area and in terms of memory. They have certain trade-offs, and actually this talk I'm going to talk about these trade-offs in medical applications. Okay, so here is a cross-section of resistive RAM device we are using. So this is fabricated by our partner LightOn in Grenoble, and we use commercial 130 complementary metal oxide process, semiconductor process, and basically that's a photograph of a single unit, a single bit of weight matrix. How does this work? First, we provide an information coming from the input or from previous neural network layer, and then we perform XNOR operation, which in turn is summed and activated. So how does it look like in a circuit? It's basically this. So you have your weights, and what is particular to what we do, we place the XNOR operation immediately next to the memory, so that basically the computation, it happens during the read of coefficients. So it's not as efficient as in your optical system, because still you need a clock cycle, but in any case, this way we indeed tend to put memory as close to computing as possible. Okay, so here is the first use case, is actually electroencephalography. So for instance, for brain-to-computer interfaces, so we need to place electrodes on a scalp of a subject, of a person, and those electrodes, they would produce this kind of time signals, and as you may already have guessed, even for experienced doctors, it might be difficult to analyze those signals, and therefore use of machine learning can be also a complementary of complementary use to current medical practices. So this kind of setup, it can be used also to diagnose epilepsy or even to predict epileptic seizures in advance and diagnosing other disorders. Okay, so all the electrodes are placed in standard locations so that we try to achieve reproducibility between person and another person. There are different advantages of this technology. So it's accessible, it's low cost, it's non-invasive, so there is no need to drill a hole in your skull. So it's not harmful, so there is no risk to drill your brain, literally. And it provides good temporal resolution. On the other hand, we have very poor signal-to-noise ratio, and we have different artifacts, so we need to use certain techniques to filter the signal and to improve the signal-to-noise quality. Okay, so how would we imagine the use of our algorithm and our binarized neural network? Indeed, very typical practice in clinics until now, until very recent, it was some sort of pre-processing, such as fast Fourier transform or other methods, and different number of this pre-processing until of this pre and then processing steps until you get the answer. But in order to avoid excessive energy consumption, we would prefer that our neural network is end-to-end. By end-to-end, I mean that you receive a signal and it provides some answer. So ultimately, it should be something like normal state or some problem, and then there should be some confidence. So that this, again, this can be used as a help for a doctor or in cases where doctor is not present. So for instance, in remote places or in developing countries, so on. Okay. So here I need to remind you the basics of modern neural networks. So a typical neural network would consist of different types of layers. So first part is so-called feature extractor consisting of convolutional layers. And the second one is classifier, which is typically a fully connected layer. So in both cases, the unit of the elementary unit of operation is a neuron. How does the convolutional neural network work? So the information is provided as an array, and there is a sliding window which computes a dot product resulting in individual output pixels, and then there is some nonlinear activation. The same happens in a fully connected layer, except that you don't have this connectivity sparsity, you have all connections. And this is our architecture which we apply to analysis of electroencephalography signals. So first we have two convolutional layers. So this is what we call convolution, one-dimensional convolution in time, and I will explain you in the next slide. And here is spatial layer combination coming from the previous layer, and finally we have average pooling or subsampling operation, and then we have classifier. So by temporal convolution, I simply mean that this sliding window now acts not in space, but actually on time points, so that like we need to accumulate some time points and in order to produce the result of computation. Okay, so this, as I already mentioned, this neural networks, they are a good candidate for binarization, but on the other hand, there will be a trade-off in accuracy. So how do we achieve that we don't lose any accuracy? So if one looks closely at the architecture, they can pay attention to classifier, which very often has up to can have up to 90-something% of total weights, and this hints that there is a high redundancy of connections of information in this layer. So here we will check two strategies. What happens if we try to binarize all the network, or what if we can get a trade-off by binarizing only the classifier. So, and indeed, we use data set from a public PhysioNet motor imaginary data. So motor imagery means that someone has to imagine if they move their left or their right hand, and then the task is using recorded EEG signal to classify what was the intention. So for this task, in the literature, we have a result of 88% accuracy on 6-second EEG recording. So this model that I have just showed has 0.3 million parameters, and 66% of them are in classifier. So now, if we look at our results, we see that if we binarize the complete neural network, we get 86% result. But if we don't want to reduce accuracy to this point, we can still gain some memory by binarizing only the classifier and getting 87% accuracy, which is already close to the neural network with real weights. So now the question is if this is just a coincidence, or maybe our result can be extended to other biomedical tasks. So what can we do? In this case, we simply check other data sets, other tasks. So another problem, which is also very important, is electrocardiography, or ECG. So typically it's done by placing 12 electrodes over the body and limbs, and the recorded signal corresponds to cardiac muscle depolarization. So this is used to diagnose different kinds of arrhythmias, and in this case we have 3-second ECG recordings, and our goal is to perform binary classification. So for that purpose, we use data from the challenge data competition, and the task is to discriminate if there was an inversion of pairs of electrodes or not, because it's known that if some physician places electrodes in the wrong order, this may lead to wrong diagnosis. So in this task, we had to detect these inversions, and to our surprise, actually we achieved very good result, which is equivalent to one of first 3 places. Actually, let me explain. So if we use real weights, we get a score which is equivalent to what's the first place, and if you binarize only the classifier, then we actually remain in this region on standard deviation. So it's already very close to the original result, and that's what gives us the 3rd place in this competition. Finally, pay attention to this graph. So in this point, we've got around 92% accuracy. It's when we use a neural network with the same number of neurons as in the original one. So we try to compensate for that by increasing the number of filters in the convolutional layer, and roughly doubling the number of neurons. And that's how we get around 94.5% accuracy. And so on, as we increase the number of neurons, we get better and better accuracy until the point where it makes less sense. So from this graph, you can see that indeed partial binarization gives us is the most promising, since we reduce the module size or the number of bits in memory fivefold, and still we get accuracy which is very close to the original model. Okay, so so far we were discussing mostly time-dependent signals, but in medical applications we have rengenography and we have other medical imaging techniques. So can we transfer our idea about the binarization trade-offs to much more large-scale benchmarks? So in this case, we took the ImageNet dataset, which has 1.2 million training images, and then we have 1,000 classes, and we trained binarized classifier on those data, and indeed what we achieve is top 1 accuracy, which is very close to the real weights neural network. So the real weights is 70.6%, and with binarized classifier it's 70%. Whereas in the literature, using the same architecture as we did, which is so-called mobile net architecture designed for mobile devices, it was only 55.4% accuracy when you binarize the complete neural network. Although in this case, the benefit of memory or of binarization is not as appealing because a classifier has only 25% of total weight. Still, we are able to validate our assumption about the redundancy of classifier connections. Okay. Finally, we were interested to, since our resistive RAM devices, they are not perfect, and we prefer to apply very weak currents so that we use the least amount of energy possible. We get bit errors, and we were interested to look how much resilient is our network with respect to these errors in weight. So first we tried a very simple benchmark, which is handwritten characters recognition, and here we started to increase the bit error rate starting from 10 to minus 5 and going to 2 to 10 to minus 1. So what we see is that at the point of 2 to 10 to minus 3 bit error, which is corresponding to hardware we have, we almost have no performance degradation. So this was done with the fully connected neural network. Okay, we take another benchmark, which is a bit more complex. It's CIFAR 10, where we have already colored images, and we already apply convolutional architecture. So this model was AlexNet, the same, which was seminal work, or which made actual neural networks very popular in 2012. So here we've got something like 88% accuracy, and which slightly degrades in this point of 2 to 10 to minus 3. And of course we observe further degradation as we increase the bit error rate. Okay, so we would like also to take a look back at ECG data, and we see a very similar trend that our binarized neural network is able to perform pretty well until certain number. So unfortunately, the news is that at point 2 to 10 to minus 3, we already get about 3% degradation. So in this case, we have to look at alternative models which might be more resilient to bit errors. So that's what will be our future work. To summarize, we would like to use neural networks for different medical analysis tasks, so that to leverage the in-memory computing approach. And for that purpose, we would like to use end-to-end neural networks. This can be efficiently applied to electroencephalography and ECG signals. And finally, which might be the most interesting to you, is that neural networks, they are resilient to bit errors. So I didn't include everything in this presentation, so feel free to ask what was interesting. Yeah, final words about our collaborators. IIT Delhi, ex-Marseille. So these guys, they are looking at actually medical images. So they apply binarized networks for vision problems in medical domains. These two institutions, they actually develop the actual hardware. So, thank you for your attention.
Thank you, Bogdan. We have time for questions, so feel free to shoot ahead.
Yeah, how do you binarize your system? You basically go from the 32, you basically, I mean, there are different ways to binarize those
right,
systems. What's your...
So I did not mention that in this work we mostly aim at inference.
Yeah.
Okay, so we train our networks on conventional non-binarized graphical processing units. But after training, we got weights which are plus or minus ones.
Okay, so basically, you have the full model, and how do you go from the full model to the binarized one?
So when we do a forward pass during training, we actually approximate the results as if we had already binary weights. Okay? It's the only difference is that when we do backward pass, we treat this as if those were real weights. So like in forward, it's always binarized.
Okay.
That's why there is no difference when you go to alternative substrates.
Is there a question?
So just to make clear, when you do the training, you are still using the propagation of the correlation algorithm, and then when you do the backward pass, you're computing the ingredients, you're accumulating the results in flow 52, and then you somehow cut them in, you binarize in some way. Like you don't do the training with binary weights, you do the training with flow 32 weights, and then after the training, you binarize your network.
So it's not completely so. So I forgot to mention when I just replied the previous question that since sine function has no gradient, or you have zero gradient basically, in order to update the weights, you approximate sine function gradient with the gradient of hard sigmoid, which is basically like this square rectangle. Okay, so like in the literature there is what they call latent weights. So latent weights, they are responsible for training. But when you go forward pass, it's always that you have truly binary weights.
Okay, and another thing, when you pass the images to your network, the weights are binary, but what about the activations? Are they also binary?
Yeah, so you have sign activations.
Okay, and the inputs that you give to your networks, they need to be binarized too? So you
Okay, that's the best question. Yeah, indeed, very often the inputs tend to keep original, so that only the weights are binarized. But actually we work here on different methods how you can avoid this. So for instance, we do stochastic sampling, so that the value of input is proportional to the real value. Okay, so like if you have 1, then of course you always will have 1s, but if you have like something like 0.5, then the probability of getting 1 is only 50%. And then we use different tricks like accumulation of those intermediate results somewhere in the network. But this way we avoid the need to provide non-binary inputs. So the point is that there is a lot of work in the literature, and we also work on avoiding non-binarized inputs so that we can decrease the area.
Yeah, we have time for other questions.
Just about binarization of the input. So if I understand well, you pass the like real inputs to a sigma in, and then sample like randomly with the value you get from that.
So we don't use sigmoid, we use sine.
Yeah, but to binarize the inputs, you say you convert the real value to a probability, and then you
Yeah.
sample 0, 1.
So yeah, basically the trick is that you need to do several iterations so that you can accumulate the results. So you can accumulate the results, for instance, after the first layer. So yeah, and then what you accumulate is approximately matching what would you accumulate if the inputs were non-binary. Because although the networks are called binary, but you have to realize that in fact, okay, so in fact,
Yep.
okay, that, okay, stop working. That in fact, when you do pop count or you count bits, you already got an integer number, a non-binary number. So in some literature, these networks are called integer networks. So yeah, thanks to the fact that we have this integer value somewhere, we can take advantage of this stochastic sampling.
Stupid question. What's the
There are no stupid questions.
Well, sometimes they're really dumb. So, what's the last layer that you have? Generally, it looks like a small number, like 80, 90, and you get into the classes apart, at least on one of them.
Do you mean how many classes do we typically have?
Well, yeah, that would be one answer. But the first part is how many features do you get before you?
Yeah, okay. So, I don't know, this sometimes doesn't react. No?
You can use arrows.
Yeah,
More
so it really depends on the model. So here you have 2500 features coming from convolutions.
Okay, so my question is, on this example of the 2500 features, have you been playing with the 80 that goes afterwards, or 80 is the number of classes?
80 is basically, here you have one hidden layer. So it's intermediate result.
Okay,
in
so
the classifier.
80 is the size of that intermediate.
Yeah, and then here it's binary problem. It's only two classes.
Okay, so my question is, have you been playing with the 80 so that you would be going to different numbers like 80,000 as opposed to 80, and see if it was actually providing you good results?
Yeah, you can improve your results by reducing redundancy in this way, but the thing is that we always try to use minimal model. So like what I presented was always what we call minimal model, so that it should be the most proximate to like actual hardware implementation. So like we always have this conflict between accuracy and hardware limits. So.
Yeah, but if you were to be using LightOn's hardware, you could go all the way to about 800,000.
Okay, so let me switch another example. So indeed, for instance, here I didn't tell all the truth, as usually happens. In our case,
No, you simplify.
in our case, so yeah, the mobile net network, it has only one layer in classifier, only linear result, right? But in actual, to get this result, we cheated a bit and we already put like one additional hidden layer to get better accuracy. So indeed, as you can get certain advantage if you increase the number of neurons in this classifier. And the same actually everywhere, including convolutional layers. So there is usually this way, especially in computer vision. If it's a computer vision problem, then at least on simple benchmarks, you always approach the with completely binarized neural network. You can always approach the result in a network with real weights just by increasing the number of neurons. But actually, this benchmark is much more complex, and you see the best achieved is like 55%. But they increased about 4 times the number of neurons. So on more complex benchmarks, the question is still open.
And one last thing, when they're doing those binarization type of approaches like MobileNet and everything, they also have constraints on the power level that is essentially being used for doing order computations. What's the figure of merit there? We talk about 1 watt, 30 watts, 200 watts. What's the constraints?
I didn't include this in the slides, but actually just go to the original work they will provide.
Okay.
Yeah, but the feature of this architecture of MobileNet is that they replaced convolutions with separable convolutions. So instead of like doing one real convolution, they first perform only like a separate convolution in each channel.
Yeah.
And then they have 1 by 1 kernel to recombine. So it's very similar to what we had in our own EEG case. Like the same here, like first you do like individual channel and then you do recombination. And this way they solved they needed like 8 times less basically multiply accumulator operations. So yeah, and then also they did this like study so that they can use only a fraction of their neurons and then how it will improve. But you should really refer to the original paper. I don't have it in my head right now.
Right. Thank you.
Okay. One last question, and we move to the next talk.
More on the hardware part of things. You said you were interested in inference, basically, and you talked about deploying your models to directly to a chip. Do you envision this chip be configurable, or built just for one?
Yeah, so this chip is reconfigurable. Because you have this resistive RAM, it's a non-volatile memory, but it's also programmable memory. Yeah, okay, so I have like, in the end, like everything that I didn't include in presentation. So I should, so usually you use what is called the Crossbar Array. And that's actually the photograph of actual device produced by LightOn. So like it depends. You can read either like one column or just one like value of information, and yeah. But the idea is that every bit here is reconfigurable.
So thank you again for your presentation. If you have more questions, once again at the coffee break after this talk. But now we are going to have Gavin, who is coming from Toronto, and who is getting us super loud. Hey Gavin.
Hi.
You're a bit loud on our end, and I think it's because of an issue with our setting up. I'm putting you on the main screen. Give me I will give you. Whoop. You can see me. I see you.
Oh wait, let me just.
Yep.
No, think about it.
Let me just on my end.
Oof, that's close.
Yeah. Don't worry. We'll move things a bit. Whoop. So we have you on our screen. You can start sharing your screen.
Yeah, I'll share my screen.
You are a bit loud on our end. I'm trying to find a way to.
Oh, yeah. I could try and turn down my mic, but.
Yeah, if you can actually, because I have no idea how to change. It's a bit of a weird setup.
Okay.
Sorry. I will
see.
give you the audience instead of me.
Oh, hi. Okay, I don't know where my mic volume thing might be. Oh, you were watching me try and find the mic.
Yeah, we are watching your screen, so it's
okay. Might be? No, I have no idea. I'm sorry. I'll just go to this. That's going to be easier.
We can do like that.
Don't worry.
I'll just sit slightly further away. Maybe that'll work.
Yeah, that will work. That will work. No problem. So, well, it's all yours for the next 30 minutes.
Okay, thanks.
You can
So hi, I'm Gavin Gray. I was previously working at the University of Edinburgh on efficient machine learning. Currently at the University of Toronto. And this is presenting some work from my thesis, which was, I just graduated into my PhD last month. And this is from a paper called, I should have put the name of the paper here. It's the one with 1906.00859 on arXiv. That's a paper called Separable Linear Transforms Enabled, Separable Linear Layers Enable Efficient Transforms or something. Yes, I can't remember. And yeah, it's going to be about efficient machine learning and kind of building on some previous work that we've done. So my current supervisor recommended that a talk only have 3 points for the audience to kind of think about. And these are my 3 points. There's lots of different linear transforms that have been proposed in the literature in deep learning over the years. And lots of these have been shown to give like 10 times improvements in the efficiency of whatever neural network was popular at the time. I wanted to kind of look at those results again and kind of compare them on modern benchmarks and kind of use them throughout the neural networks. So when I did this, I found that these overparameterized neural networks, you can use a lot of these efficient linear layers all the way throughout. Unfortunately, lots of new architectures can achieve similar results. Because if we think about things like architecture search or like efficient net, which I think is also found by architecture search, they come up with these incredibly complicated block structures, and they end up kind of breaking the single linear transform into lots of different little linear transforms that they then sort of join back up together, which kind of changes the way that we might think about like substituting in efficient linear layers. So, yeah. So why do we want to talk about linear transforms? Well, let's be clear about what wording we want to use here. A linear transform is a matrix vector multiplication, and if we add a bias to that, that's an affine transform. In most deep learning frameworks, they're going to call this a linear layer or a fully connected layer. And matrix vector multiplication is order n squared operations and order n squared in the number of weights that you have to store. And this is almost every part of deep learning. Like most parts of deep learning are going to involve doing some kind of linear transform all the way through, like all your convolution layers, all your linear layers. Yeah, as I was saying, most neural networks are made of convolutional layers. If we would say this is a ResNet, most modern architectures are kind of inspired by a ResNet, and they have a very large number of layers. All these layers are convolutional. It's important to start thinking about how we can make all of these layers more efficient. And just to kind of clarify that point, most convolutions are implemented by a M2 called GAMM, which is you take your input image, you turn it into a big matrix, and then you do a matrix multiplication between the input matrix and the kernel matrix, which is your weights. This is like how most frameworks are going to implement convolution. And thanks to efficient matrix multiplication algorithms, that is actually pretty efficient. And this kind of becomes even more clear when we think about in most efficient neural networks, we're going to be using something called separable convolutions, where first we split our input tensor into three different channels, process all the channels independently, and stick them back together and apply a pointwise convolution at every point in the input space to reduce our output tensor. This is kind of what's happening on the left here, and then on the right is the pointwise convolution. And the pointwise convolution is just a linear layer. I mean, you can kind of think of it as applying a linear layer or a fully connected layer at every point in your input space. And we kind of care more about the pointwise convolution rather than the group convolution here, because the pointwise convolution is the one where you're going to be using most of your storage space and most of your processing power, because typically will have a very large number of channels, and it's going to be n squared the number of channels. Having more different efficient linear layers that we can kind of count on to use in deep learning seems like a useful thing to kind of motivate, because it doesn't just mean we're going to be more efficient at test time. This isn't like something where we train a neural network, we do something to it to make it more efficient, like sparsifying it or binarizing it, and then we produce a more efficient neural network. This would affect training time as well. We'd have efficiency benefits like all across the board. If it just turned out we didn't have to use full dense weight matrices. It would give us a bigger search space for architecture search, which arguably they don't really need because they can't hard to even search the ones we have right now. It would make larger neural networks possible because it would be more efficient at training time, so you'd be able to fit larger mini batches in. And then it would also make completely different types of deep learning possible. I think this workshop's organized by LightOn.io. They're doing work I remember seeing like years ago in the ACDC paper. They were citing the work on efficient neural networks in optical systems. So I think you're all familiar with that probably, but there's also like tensorized neural networks, invertible transforms. There's like lots of exciting different ways we could implement linear layers that would allow different parts of deep learning to do new things in exciting ways. So it's kind of probably worthwhile thinking about how we might do this. So I'm going to do this kind of a comparison of different low complexity linear transforms in just an empirical way. And these are the 6 different linear transforms that I'm kind of thinking about. Now I'm going to go through each of these and explain what they are in later slides, but this is the list and citations for each of them. We got rank, factorize, decomposition, ACDC, tensor train, Tucker, hashnet, and linearized shufflenet. They're all quite different, but that's because I want kind of a range of different approaches. And you might say, well, these papers already presented empirical results. Why do I need to compare them again? We could just look at those papers and figure out from what they present whether it's useful. Well, a lot of these results were taking AlexNet or some other network like AGG, and then replacing the final fully connected layer with their efficient alternative they were proposing, like ACDC did this, for example. And the trouble was, it turns out you can quite easily replace those final layers with almost anything more efficient. You can sparsify, you can binarize it, and in fact, there's more recent work showing you don't need those final layers at all. And if you look at, say, ResNet, as I said earlier, and a lot of other modern architectures, they don't have these huge fully connected layers, where like 90% of the parameters are 90% of the compute goes. They use their compute all the way through the network. So these results maybe don't transfer to modern networks. We don't really know whether any of these methods are going to work. And deep learning involves applying a stochastic gradient optimizer and kind of hoping that it'll converge. It doesn't mean that we can just say, oh, this is definitely going to transfer and work, along with especially new training techniques as well. Batch norm changed everything right when it came out. So rank factorized decomposition is kind of the dummy decomposition in this sort of example. It's the simplest one you can imagine. You're just implementing a linear bottleneck where you first pass your input into a lower dimensional space and then project it back out of that lower dimensional space. It's obviously more efficient because you're only storing 2 smaller weight matrices rather than 1 large one, and you can obviously use less compute as well because each of those weight matrices takes less compute to process. So that's kind of the simplest alternative. But if it works as well, then it's kind of interesting, right? ACDC is a circular transform where we're building up a linear transform by just taking diagonal matrices, discrete cosine transforms, and permutation matrices, and stacking layers of these over and over again. And it seems like kind of an odd thing to do when you just state it like that, but you can kind of motivate this in terms of circular transforms according to a theorem which I'm not proving here, but I'm going to state. saying that if these were Fourier transforms and you stack these permutation matrices and diagonal matrices together, you can approximate any linear operation in complex space to arbitrary precision. In practice, we're not using Fourier transforms, we're using cosine transforms, but we're just going to hope that it kind of applies anyway. And there's various papers using circuits and deep learning, but I sort of thought it'd be more useful to build on the older work. And the complexity of this is quite a bit better in theory, because when you're implementing a cosine transform, you can use a fast Fourier transform algorithm, which is n log n. So obviously that's going to be quite a bit faster. And you only have to store however many diagonal matrices you store, which could be order n. So it could be a lot faster. In practice, I found some problems with this. But yeah. HashNet is completely different. HashNet was a paper showing a method of using weight hashing in your neural network. So you have a small number of real weights, which are shown at the bottom of this figure, and you're going to build a virtual weight matrix by just indexing these real weights and placing them in your virtual weight matrix. So you only have to store a small number of real weights, and you get a full dense weight matrix that's hopefully has all the properties of a weight matrix that you need for deep learning. This is kind of a more mathematical statement of what this involves. You're indexing your real weights with the hash function and producing a virtual weight matrix. And we're hoping this hash function is very cheap to compute, and it can be in practice, like it's been shown in the original paper. Now this, you can ask me, why would this work? So there's many papers using random embeddings as a way to kind of, and feature hashing techniques to kind of reduce the dimensionality of high dimensional feature spaces. And there's even like very successful machine learning projects called like Buffle-Wabbit. I almost get that one wrong. Buffle-Wabbit's kind of large scale machine. If you've got like billions of features and you want to, like, is it billions or millions? Millions of features, and you want to learn some kind of function that will predict things from those millions of features. It's a product developed by Yahoo years ago to do that, and reportedly worked quite well. It was famous at the time. And yes, it approximately preserves inner products. So you might hope that since we're basically doing inner products all the time in deep learning, this would approximately preserve whatever we need to be able to do to make deep learning work. The complexity of this is actually kind of a different case, because since you're building this virtual weight matrix and it's a full dense weight matrix, you're still doing the same number of operations if you just stored a full weight matrix. So it doesn't save you any processing power, but it means you can store the network in a lot less space. So that's kind of useful. Tensor decompositions, I'm not going to describe it in much detail. I implement them in a fairly simple way, just taking a high dimensional, and in most cases 4-dimensional tensor, and reshaping it down to a weight matrix. I'm just kind of interested in to see whether either of these tensor decompositions can store useful weight matrix. This might be badly, not the best way to do it, but it's something. And I was hoping to kind of come up with at least one which sort of already had empirical results in this kind of space of replacing all the linear transforms in a deep neural network. I think ShuffleNet presented like quite a good opportunity for that, because if you look at this, this is a breakdown of the 3 different ShuffleNet blocks that they used in that paper. The one in the middle is the one that I was kind of building on. And if you ignore the relatives in this, it's actually a fairly similar linear transform to, say, something like a block diagonal AC/DC kind of transformation, because you're doing a one-by-one grouped convolution, which, when you think about what that is just a blockwise weight matrix. So you'd start with a blockwise weight matrix on the left here, and then your riffle shuffle, which is what they have here as a channel shuffle. Your riffle shuffle then shuffles this sort of block diagonal matrix into these columns. And then when you apply another block diagonal weight matrix, you end up with this random weight matrix, which connects everything in a kind of, with a kind of random weight matrix that kind of looks like something that might be like a dense weight matrix that you might use. And in practice, it works, because and you already know in practice it's going to work because it's the same thing that they use in their paper, so we should expect that it will work. And it's also fairly efficient because you only have to store order n squared over g parameters and use the same order n squared over g operations. So it's kind of nice to have something which already has some empirical results. Now, comparing these linear transforms, I wanted to compare these in the simplest way I could, and in deep learning, the problem which kind of originally popularized, or repopularized deep learning, if you want to say that, was when AlexNet did very well on the ImageNet benchmark. Now, I think that's kind of a fairly good place to start as a way to compare deep learning methods. If you want to prove that your efficient neural network can perform all the things that we would hope a deep learning system would be able to do, showing that it can solve ImageNet well is a fairly robust way to test that. Unfortunately, I don't have the processing power of Google behind me, so I'm also going to do experiments on CFAR10 and hope that those kind of transfer to ImageNet. And that's something I guess I'll have to discuss. So in these experiments, there's two kind of training methods that I use to kind of make these things converge more easily, and also to reduce the number of experiments that I need to do. The first of this is a way of scaling the weight decay, and the second is a kind of distillation method. Now, I did not want to have to do a full hyperparameter search over weight decay settings, because I was already doing different settings for the different parameter budget settings for each of the alternative linear transforms. So if I then try to use different weight decay settings for every single one of those, it becomes multiplicative. And I could never do all of them on the processing power I had available. So I needed to find a way to set the weight decay for each of these things that would make sense. And I did some experiments, which are kind of more detailed in the paper, about how to set this, and came up with this kind of rule of thumb first thing, which is just to take the weight decay and multiply it by the compression ratio that you're seeing in the network, which is kind of simplistic. Like, say you're reducing the number of parameters to 1/10 of the original, you use 1/10 of the weight decay. But in practice, it works quite well, and it seems to have the nice property that once you're training the network at full precision again, you're going to use exactly the same weight decay setting you would have used originally. So it's kind of like, it reduces back to the original thing. And there's a recent paper came out after I worked on this called butterfly transforms, where they do a similar kind of efficient linear transform alternative, placing it in place of the pointwise convolution in the same way that I'm talking about doing here. And they found that the same thing, that they had to reduce the weight decay to make this converge. Now, I also didn't want to have to tune any other parts of the hyperparameter training process. And I knew that I would have access to the full precision network whenever I was training any of these alternative linear transforms, because I'm just taking this full precision network and using the same architecture with pointwise convolutions substituted with this sort of compressed linear transforms. This means that I can quite easily use kind of attention transfer distillation, and it's not going to slow down my experiments very much. I think it's not too unreasonable to sort of talk about this as a training schedule, because in practice it would involve just training your network twice. You would train a full precision version of your network, and then you would train an uncompressed version of that, a compressed version of that network using the original uncompressed version. In practice, I did an inflation experiment, just trying out what would happen if I hadn't used this. And it only makes like a small difference, like 1 or 2% in accuracy. But I found like it stabilizes training and kind of makes it easier for me to run a large number of experiments without having to do too much hyperparameter search. So I wanted to choose architectures to kind of use for these experiments that are are representative of a lot of networks that are currently popular. So I went with kind of wide ResNets because they're just effective versions of ResNets. They're slightly more effective than ResNets, and most popular architectures these days are based on ResNets. But I also wanted to kind of look at state-of-the-art networks, so I thought Darts on CFAR10 would be a good choice for this because it was, at the time, the state-of-the-art for CFAR10. And I wanted to choose kind of state-of-the-art efficient network for ImageNet, so I thought it would be worth doing an experiment with MobileNet v2 to kind of show that whether or not this method would still kind of work there. So the kind of more impressive result that I have in this paper is to show that if we're taking a Darts network and we're replacing pointwise convolutions with these different alternatives for various different budget settings and for various different substitutions, we achieve fairly similar results in compression, and we get to this sort of nice place in the space which doesn't seem to be very well explored for like efficiency in neural networks, where we're achieving like less than 4% top one error and using less than 1 million parameters on CFAR10, which when we saw it, we were kind of excited about it. It looked quite good. Unfortunately, AC/DC substitutions aren't on this because I had some problems implementing them in the Darts network, being just with a large number of pointwise convolutions, some numerical issues trying to get it to work. And we saw similar results with the way that ResNet 2810 on CFAR10. This sort of shows a compression of about 10 times, even for the sort of largest budget on the far left here. So we're showing the number of parameters versus the top one error here. And the original network was 30 million parameters, and the top of this figure is about 3 million parameters. So the compression rate is quite significant for a fairly small drop in top one error. This figure does have some results for AC/DC, but only for the smallest budget settings. As I increased the number of AC/DC layers, I started to run into numerical issues back propagating through large numbers of AC/DC transforms. I think there'd be better ways to implement it than the way that I did implement it in the code, especially because it's an invertible transform, so you wouldn't necessarily have to store the activations, but I think by default it would do that in PyTorch. Now, when we move to ImageNet, the results we get are no longer like state-of-the-art. Here we're showing the size and the number of parameters versus the top one error on ImageNet, and I've kind of placed various networks in the literature on here to compare against. So the colored lines here are the different networks I tested on ImageNet. I had limited compute power, so I wasn't able to do the number of experiments that I did in the previous case on WRM 2810. So I only included a TensorTrain, HashNet, rank factorized, and ShuffleNet. There's two cases here called HashNet plus linear and ShuffleNet plus linear. Those are just cases where I also replaced the final linear classification layer with a more efficient alternative, using a HashNet or a ShuffleNet decomposition. Just because those two were kind of the more interesting results here. ShuffleNet substitutions in particular is the kind of light blue line here, and it seems to suffer less from using a smaller budget in the number of parameters compared with the rest of them. Whereas, rank factorized, as we might hope to see, the simplest thing possible does perform quite badly. And this is looking at the multiply adds, so a decent way to measure the kind of amount of processing power you require to implement your network. And you can see here the HashNet is exactly what you would expect to see. It doesn't reduce the amount of processing required at all. The kind of flat line here, regardless of the number of parameters you use. Whereas the ShuffleNet rank factorized decompositions seem to allow some amount of reduction in the number of multiply adds. The original network here is the WRN52. It should say that, I guess, more clearly, which you can see as a 10 to the power of 10 multiply adds. So we're losing like 10% top error to reduce that by 10 times using shuffle net substitution, which is not nearly as good as the results we were seeing on CFAR 10. And then looking at MobileNet v2, there is kind of, I wanted to do an experiment with a state-of-the-art efficient neural network. On the left, we're sizing parameters against top 1 error again, and the colored lines here are the results from the MobileNet papers. So we've got the blue line, which is MobileNet v1, the original paper, MobileNet v2 is the green line, and ShuffleNet is a similar paper. The original ShuffleNet paper is a similar paper in efficiency. And they all track this fairly similar line in kind of parameter versus top 1 error space. Now, the result, which is maybe not that satisfying, is that when we substitute pointwise convolutions in MobileNet v2 with a ShuffleNet alternative and retrain the network, it ends up performing just as well as we would imagine MobileNet v1. Sort of this red dot here just lands on this blue line where MobileNet v1 seems to perform. So if we just scale the number of channels to MobileNet v1, we would expect we'd achieve a similar result as kind of doing this linear compression substitution. So in summary, I'm going to repeat the points from earlier, but with different words. There are many different linear transform alternatives you can use in deep learning, and many different ones that have been proposed. We can substitute these into neural networks by replacing pointwise convolutions or just replacing convolutions with these more efficient alternatives. And it will probably train, and it may even match the performance of existing deep learning networks. But I would say on large problems, the performance doesn't seem to really care about the architecture that much. If we go back to this figure, I remember the first time I plotted this, it was quite interesting to see. There's a very clear kind of Pareto curve between all the methods published in the literature, the WRN52 down to the 0.25 MobileNet. And you can see that there's this sort of parabolic relationship between the number of parameters and the top 1 error. And you can kind of see it again on a much smaller scale. It's a very clear line, regardless of whether it's a ShuffleNet or MobileNet. They've both tracked this performance versus top 1 size versus top 1 error line very clearly. So it could be that, as we do more architecture research and kind of come up with new neural network architectures, we're just going to get kind of stuck at this line depending on the number of parameters with current methods. So yeah, thanks for listening to my talk. This is all work done at University of Edinburgh with Elliot Crowley, Jack Turner, and Amos Storkey. There's another paper that I was working on with Jack Turner, who's the lead author, called Plots, which is also kind of interesting, but haven't presented here. I'm currently in Quaid Morris's group at the University of Toronto.
Yeah, so we'll move to questions. Does anyone has any questions to start with? And the mic is not working, it's not charged, so try to speak loudly, and if Gavin, if you can't hear, tell me and I will just repeat the questions.
Okay, that works.
It looks like it's out of the scope of your work here, but have you tried any of these efficient linear layers on transformers, for instance, where there are many linear layers?
Did you hear anything, Gavin, or do I have to repeat?
I got some of it, but not enough to understand.
So I think the question is about, have you tried these techniques on transformers or other architectures for neural networks?
I haven't tried it on any other problems apart from image classification, because it's kind of the most heavily benchmarked task. It would be interesting to see yeah, it would be very interesting to see how these kind of methods would work, because I haven't seen that many works kind of compressing. Like you could imagine like huge things like BERT or like GPT-2. Those things seem ripe for like mono compression, definitely.
Another question, maybe? You won't have a chance at the break, so it's now or never. No? Okay. So thanks a lot, Gavin. It was very interesting. And that's it. So thanks again. And well, bye, Gavin.
All right, thanks. See you later.
Can I shoot it off or not? If I can find my mouse. Whoop. Okay. So we are going to have like a short coffee break at 10, 15 minutes. Something like that. And
10 minutes?
yeah, so let's 10 to 15. Then when we come back, we'll have David Busso's team will talk about using the OPU for particle physics, and then another talk about matrix factorization with random projections.
Don't worry. You have more problems. Yeah. Sorry for the camera. I don't know.
Oh, don't worry. It's okay. I mean, we do it for
For fun.
yeah. It doesn't matter if you can't see or. Yeah, sure. Let's put this.
collide, you have more interaction. At the same time, it's called a pile-up. And obviously, it makes things harder to discriminate between the particles. Okay, so that's the collider part. And now we want to detect those particles, classify them, and say stuff about them. And to do this, we have accelerators. As I said, we are mostly working on Atlas. This one is from CMS, but it works the same. So here you have your beams. The collision takes place around here, and then you have this huge stuff. Here you can see human being for reference. That aims to detect the particles. So how do you do this? Well, here you see a slice of a magnet, and the magnet will curve the charged particles. So if you have positively charged particles, they will go in one direction, negatively in one another. And so already you can have the charge of the particle. Then the curvature gives you more information, because if a particle has more mass, it will curve less. If it's faster, so has more energy, it will curve less too. And it will allow us to assess something called the momentum, which is more or less, physics would kill me, but the product of the mass times the speed of the particle. So already you have the first part, you see, you have some, it's called a tracker. You have several layers, and in each layer you have some silicon sensors, not unlike the ones you have in your phones. And each time a particle crosses those trackers, it leaves a track, so a three-dimensional point. And if you can connect the dots, then you can hopefully track back the track of the particle. Then on the second stage, you have something called calorimeters, and those, as you see, will just destroy the particles, and this allows to register the energy of each particle. So tracking to get the momentum, calorimeters to have the energy. So here from electromagnetic particles like electrons, here for hadrons. Here you can also make things with muons. In the first part of my talk, I will focus on the tracker, and then the second part by Biz Vajit will be on the calorimeter. Okay, so just to give you a few numbers, that's the amount of data we have at the LHC each year. There is an upgrade plan, and currently we have an average pileup of 50, so 50 collisions each time. We expect it to be 4 times the same. And in the next generation, we'll have 10,000 particles per collision. So in the tracker, you will see 100,000 three-dimensional points. And the goal is to retrieve the track of the particles that give birth to them, and knowing that you not always have the same number of hits per particle. And well, what we're currently trying to do now is it won't scale with the current methods, so we try to look for innovative data analysis method for the next generation. And well, OPU was one of the things we investigated. Okay, so just for the tracking part, I would have 3 subparts. First, I will present the dataset that we use for tracking. Then I will present a use case we made only with one particle, see what we could do with this, and then with several particles. So yeah, just to remind you the general picture, what we are trying to do, we have some hits like this in our detector, and the goal is to find back the particles that gave rise to them. The human eye is really good at doing this, computers not that much, and well, here you say, okay, it's still doable. What we're looking at with all of our points is this. And so you have 100,000 points, and you want to do this, which is to recover the orange lines. We made a challenge to find for innovative solutions, first on Kaggle and on Codalab 1 year ago. We found interesting results, and as I was saying, we're not trying to find more innovative ways to solve the problem if possible. But in that case, with a full data set, so we just took the same data set, it existed, we ran into several problems. the thing is, it's really hard to cast the problem we have in terms of being solved by the UPU. Just as a reminder, the UPU is kind of random matrix, so you just find a way to binarize your data into 1 million bits, then you put it through random matrix, and you have random features, and from them you can have a linearized problem and say things. And to do some following, it's not really easy, especially given the amount of information that we have. In fact, for this challenge, we are thinking maybe to compress what we saw in the electronic channels, but you have 2 billion electronic channels with 100,000 hits, and you want to compress this to 1 million. We tried several stuff, TSVD, autoencoders, it didn't really give anything interesting. Well, maybe today we had a few more ideas with SVM and stuff, but still it looks like it will be hard to compress that many information to be relevant. So what we did is to use a more manageable data set, and prior to the challenge, we had used a really simplified data set, which still allowed to test some tracking solutions. And it looks like this. So you have small tracker-like geometry with 9 layers, and you can record the points made by typically between 3 and 30 particles. And the question we asked was, given this configuration, how can the OPU be of use to us? So first we tried easy case, which is 1 particle, and one particle here will have mostly 2 parameters that we try to assess. First, as I was saying, the momentum, that's the curvature, that's the inverse, link to the inverse of the curvature of the particle. And second, the angle from 0 to 2 pi. And we ask ourselves, if we have just those points and we feed somehow the OPU with this, what can we tell? So, interestingly, with this device, it's really, you do things in 2 parts. First, you have to find a smart way to represent your data, and then you ask questions to data. Here we have 500,000 pixels. That is roughly half the numbers of the input matrix of the OPU. So each pixel is represented on 2 pixels on the OPU. See, so you have the blue, orange, green layers, etc. So here blue, orange, and etc. And so you have your bunch of points, and each point corresponds to a pixel. And each time we encounter 1 point, we change the value of the pixel from 1 to 0. Here the aim is to have roughly 50% of the pixels hit to have a good response from the device. And having this, so we put it through the device, we have a bunch of random features. We take 5,000 of them, and we make a ridge regression. So we take our features, we know the truth angle that we are finding, and the question is, from this, can we recover the angle? And so here is the results. It's what is predicted as a function of the true value. I will go fast because we have 2 presentations to squeeze into 30 minutes. But the thing is that it kind of finds the parameters, so we are quite happy with this. Here you have the residuals and the uncertainty. Whatever. Then we try to do the same with the second parameter, which is the momentum. More precisely, the curvature, which is remain u proportional to the inverse of. So the curvature is inverse of the momentum. And once again, with a single particle, we actually managed to recover from the random features the original value of the momentum. So we're quite happy with this. We're not sure that's always a problem. We find stuff, we're not sure it's relevant for real physical analysis. In the second part, we upgraded to the whole event of several particles, and we took inspiration from this particle that used devices similar to the UPU, actually also the UPU, to try to predict to predict a series. And how they did this? Is that they used half of the DMD to encode the input, as we did, and the other half they reused the output of the DMD to make some kind of recurring neural network, some reservoir computing, and it worked. It worked well for them, so we tried to do something similar. And so what we did is the same. We take one layer. So this time we take all hits from one layer, and each time we see one, and we change from 1 to 0. So and the second part of the DMD is used. So it goes through the DMD, and the results from this are binarized. You see from the whole channels, and we do this for the next layer. And we hope that each layer will keep a memory of everything that happened before, and that we can use this to do predictions. So again, the encoding is made, and now we ask questions using ridge regression. First question is, so all the questions I ask are on the last layer given the results from the previous one. And the first question I ask myself is, okay, are the random variables even able to predict the number of hits that we will see in the last layer? And as you can see here, unfortunately, it's not that good. I'm probably running out of time. So, okay, this one is complicated, but okay, do it nonetheless. Here is if you expected 17 hits, that's how much were predicted. So the statistic is low, but you see that it predicted usually that probably you would have 14 hits, then 12 or 13, and the real number was not that great in that case. I mean, it was far from statistics. Sometimes it was better, but you would expect, so that's the rank, and if in a perfect world you would have a diagonal made of ones, because it's the most often seen value, and it didn't work that well for this, so it was a little bit disappointing. Weirdly, if you assume you have an oracle that gives you the number of hits that you would see, if you have this, and you say, okay, I have 3 hits or 5 hits or whatever, you have this on layer 7, where are the position on layer 8? So that's, up here you have the true value on layer 8, on test events, obviously. Here is what is predicted, and you can see that, well, it kind of works. It just outputs 3 numbers that more or less correspond to the real value. Here, actually, it's not that great because we didn't have a lot of events having that low a number of hits. But if you increase the number of hits, you have more statistics, and you see that the standard deviation of the position of the hits predicted are fairly good. If you take, for instance, 16 hits per layer, so you can see that it predicts their correct position, so predicted versus true. And well, you can see again that you have straightish lines. Okay, this one is, for instance, really good. It predicts the position. You have some that are not that good, but we are surprised to see that it just pops in the right order, the position of the hits using random variables. Okay, so for my conclusions, really, as I said, it's not easy to cast a tracking problem in terms of using the OPU, especially the real challenge that we'll be facing in next generation. Dimensional reduction is a huge problem. On the smaller data sets, we have some interesting results. I mean, we can estimate the true parameters of one particle, and even if we go to several of them, we have a vague idea of the number of particles, but mostly the projection on next layer gives the position of what we expect. So yeah, the OPU does something that makes sense, even though so far it does not match the more traditional method that we use. We'll now give the mic to Bisajit for the part on calorimetry.
Okay, so firstly, tracking is by nature it's a clustering problem kind of. So you have a number of hits and then you try to cluster them. But the Opio is more suited towards doing things that are that involve classification. So instead of problems that involve clustering, we now look at more suited problem statements which involve event classifications. Now, the first question is, where does event classification come in terms of the LHC and particle physics? What we try to do with the LHC is basically involves two different goals. Firstly, we try to test our current theories with greater precision. Secondly, we try to look for deviations from our expected models, and we try to look for new physics, let's say. So the main part of any such analysis involves event classification, where we try to detect rare signals. In this particular analysis, we'll take a test case where we try to detect RBP SUSY signals. So it's basically a new theory, let's say, and we try to look for signals that are in support of this theory and which are a bit different from our standard theories. And for that, we have simulated, the data has been simulated using Pythia and Delphis, and I've linked the talk where they talk more about this data set, but I won't go into that over here. So how do we do it generally when we have physics data? What we do is we first build jets. Jets are narrow cones of particles. So once we get those narrow cones of particles that come out after there is a particle collision, as you can see here, there's a particle collision and a number of jets are coming out over here. This is one, this is one. So once we have these jets reconstructed, we use BDTs to classify based on the jet parameters. So jets are basically, you can think of them as feature generation, like we have convolution features, we generate convolution features with CNN. We build jets for the features using domain knowledge of physics. But now that we live in the deep learning era, we try to use more theories, more architectures that involve things like convolution neural networks. For that, what we do is that we can represent the calorimeter data as a 2D image. Now, the calorimeter is basically a cylinder. So the surface is a 2D. It's 2D, so we can just slice it open and represent that in a form of an image, a 2D image over here. So what this allows us to do is that we can train more complex architectures, such as convolution neural networks, but they come at a cost. Firstly, it's computationally expensive. It requires large amount of training data, and we tend to overtrain on simulations. You see, there are obviously minor differences between simulations and the real data. It cannot be exactly the same. And convolution neural networks kind of doesn't take into account any of those. So once again, this was our problem. We have images that we are trying to differentiate between signal and background. And it's 64 by 64, and each pixel basically represents the energy value in the calorimeter. Okay, this is the Opio workflow. I don't have much time, so I can't explain how exactly the Opio is working, but the general workflow would be, we have the data, we binarize it, send it to LightOn server, get the random features, and train a more simple classifier such as the ridge regression, let's say, and make our predictions. So the first step that comes is converting our data into binary. And for that, we have chosen this encoding scheme where we have 3 equi-sized bins over here, and we have a representation for 0. Now, why we have chosen this encoding scheme is that it kind of ensures that there is more energy going through the DMD, because as this energy increases, the number of pixels that are turned on increases. So the more the energy in the calorimeter, the more energy we have in the DMDs. And it performed better than autoencoders that that LightOn already has on their backend. But the problem is with autoencoders is that when we train autoencoders, it introduces the encoder loss. So the overall loss of our model would be a product of the encoder loss and the classifier loss. When we do this, we involve no training, so we do not have an encoder loss over here. So we just have the classifier loss. But to train a simple linear classifier, we use this simple single output, no hidden layers neural network over here. And basically, this is a linear layer, but we could have done it using ridge regression. But ridge regression runs out of memory when we have a very huge data set. So it's not really scalable when we do it with scikit-learn. So that's why we had to shift to this network that we used, made with PyTorch. And the predictions. As you can see over here, that the linear classifier in the native space did not really work well. So the Opio is performing its task to make the data linear. And few more comparisons is that over here, all that you see are convolution neural networks and more complex architectures. And over here, if you look, you have at the bottom BDTs built on the raw pixel data. So in the previous slide, we compared it to a linear classifier, and we saw that the Opio was performing much better. Next, we have the Opio's performance over here, and this is a more complicated architecture using BDTs on the raw pixels. And the Opio's performance was better than that. But it does not really perform well compared to what we usually do in physics analysis, is that we build BDTs on the jet variables. But then again, on combining both of these, we get a better result on LGBM along with the Opio's. But still, it might look disappointing that it did not perform as well as the convolution neural networks. But there are, I'll come back to a comparison with convolution neural networks a little bit later. And over here, what I try to show is that on increasing the number of training images, the optimal number of features that we require increases. So, and more importantly, this curve, it performs really well with even very low number of images. And this is the problem with convolution neural networks. It requires a large training data set. This was trained with just 50,000 images, but the original networks in this image, they were trained with 400,000, and there's a big difference in that. So we test the performances in a very low data set range. Over here, we have only 4,000 training images. So, and remember, we had 64 by 64 images. So there were for exactly these many number of pixels in our image. So the number of pixels over here equals to the number of training events. And the Opio's performance is very scalable, and we still see improvement over here and also over here, where we have just double the number. But for convolution neural networks, if we go down to such a low range, well, I'm not sure, I'm sure that it won't perform very well, but we haven't really done the exact analysis, so I don't have the figure over here. And this is another thing is that since our data is along the cylinder, we can basically shift where our phi equals to 0 starts. So as an argument, you can say that, okay, I have just 4,000 images, but I can still do data augmentation by changing the phi is equals to 0 value. And I will get new data, and I can increase my data set. But over here, what we have shown is that if you pick the column with the highest energy and just set it to 0, that is, you get rid of the phi invariance. Remember, previously, if you see along this axis, the data is more or less symmetrical. But if we change this symmetry, if we just pick the column with highest energy and put it over here, right at the start, we expect the data to change a lot. And what we see is that the performance increases when we get rid of this phi invariance. So even if by data augmentation we can generate new data, we can still offset the advantage of data augmentation by doing this transformation. So finally, to conclude, I would like to say that the Opio is much faster than the CNN, and obviously for training. And the performance is fairly good in the very low limit when the number of training images is much limited. And the variations between simulated and real data is taken into account because remember, we had trained it in bins. So even if there is a minute difference in the energy values, it will be taken into account because it's a large energy range that has been binned to the same value. And it also takes into account information that other physics variables do not, because we have the raw physics, raw data from the calorimeter. So with all these knowledge, we plan to move forward by using a data set that's more suited towards the Opio's performance by all our analysis and how we understand it. So it works very well where the number of pixels compared is more or less equivalent compared to the number of training data set. So in the future, we plan to extend this technique to a similar problem, which has a finer granularity. That is, we have larger images. So that's what we plan to do next. So thank you. And
okay. So do you have any question for either actually of them or for other people from the team who have not talked? Yes.
For the classification problem, have you considered doing some transfer learning, like using the Opio after some?
Yeah, we have tried that, but we didn't really get very good results. And I would say that like the results were somewhat comparable, but a little lower than what I just presented. And our personal reason behind our logic behind it is that when you use pre-trained models, you expect them to perform very well if there is some kind of similarity. Like if you have trained network that are trained on animals, you can expect them to perform in a much smaller subset, but in a similar problem, let's say. But if you try to compare it with over here, where the problem is completely different, well, I think that's the main reason why we didn't see a very good improvement with transfer learning. Yes?
When you encode the thresholds that you picked for zeros and zero and so on, how did you choose them? It's heuristic or just?
The bins are equisized, basically. So I'll just. So these three bins, they are equisized. So the number of pixels that fall in this energy range equals to the number of pixels that's in this energy range. So we just have equisized bins, and we have one for x is equals to 0. Obviously, most of the data is 0, so I have excluded it in the distribution plot. And the other bins are basically equisized, so we have not done any fine-tuning or anything with that.
And when you pick the encoding, you encoded them with like three bits, no?
Yeah, these are the 3 bits we are encoding it.
Like for states, maybe if you use like 2 bits and you use the zeros, so 1, 1, 0, and 1, 1.
Yes, we did try that, and the performance with this was much better, actually, because that included too many states and like more bits and less number of states. We tried that, and there was a significant improvement in performance. And also, as I said, this kind of gives us a physics sense that if we have more energy in the calorimeter, we have more energy in the DMDs.
Yeah, those can be learned potentially, as Laurent was saying. Today is December 19th, and in about 6 days it's going to be Christmas. What would be your wish list for an OPU++?
Well, like for example, as we had the problem with tracking is that firstly we had to get the entire detector data into 1 million pixels. So that's one thing. If we could increase that number.
To how many?
Yeah, what's the number?
Ask Santa.
So
If
Santa.
you don't give a number, we can't give you it.
I think for the whole problem it would be quite difficult because, as I was saying, we tried to squeeze 100,000 bits coming from 2 billion channels into 1 million bits. So ratio for now of 1 to 10, it's not manageable. If we, I don't have a sense of what would be the minimum number of bits.
10 times larger?
10 times would be, yes. I mean, a lot of magnitude is otherwise.
Then there was also the fact that
sparsity is one big concern we have. That like we're representing it in this way so that there's a lot of light going into this. So if
it's more robust to change, to smooth change.
yeah, so I guess I don't know it's possible better camera or some I don't know. But if like it can be sensitive to more like small changes and like sparsity, it would be interesting. Yeah, like a bigger thing would definitely be nice. Is there anything?
You were not prepared for that question.
So what I understand is like you do ridge regression on the Opio feature.
Yeah.
So have you tried like some kind of online learning stochastic gradient descent scheme?
Well, that's something that we plan to do next, and we want to do things like that.
Okay, because your data is coming from simulated or real data?
Yeah, it's simulated.
Okay.
I think we're wondering, listening to the first talk, whether SVM network scales later or
Yeah.
similar as ridge regulation.
But I mean, you put the OPU stuff into a BDT, but only the output of the final after the
Yeah.
regression.
Yes. More a physics question. You explained like in the first presentation, you explained like first you get the momentum and then after that the energy using the calorimeter. But the calorimeter itself, whatever maybe it's not a boom calorimeter, maybe very sophisticated, itself is constructed of particles, meaning protons and neutrons. So, or do you consider that as a rigid lattice, so there's no scattering or diffraction, or how is that? It's more like a understanding of what is the physics.
Right, there are lots of questions we get. The answers can range
Does that
from a
itself
few sentences to one
scattering
sentence. Scattering, yeah, scattering you have in every layer, for instance, of a tracker, and they are full, but they can
Yes, the thing is we have many particles and the particles they overlap in the parameter. So it's in many cases that's what we took with jets because we cannot say okay, assign energy position to separate particles. They're all lumped together in a bunch of particles going
like a lattice or something like that?
So it goes into a bunch of cells, and there is while for the tracking we already measure one by one particles. In the calorimeter they are often lumped together. So that's why it's complementary of the two approaches. And in the calorimeter we can measure neutral particles, while in tracking we only measure charged particles, and half of the energy, of the flow of energy is neutral. And only be seen in the calorimeter, which is our precision, while tracking is very precision. But this is
I'm not sure I understood how you combine the jet features with the Opio.
That's basically I'm taking the output of my ridge regression, let's say. So I have the output of my ridge regression and I include that as a feature in my BDT. So that's basically like I'm training my BDTs including the output of the final output of the ridge regression.
The ridge regression that was trained by itself.
Yeah, yeah. So they were trained separately. First I did the ridge and then I fed it into the BDT.
That's it? No more questions? Oh, one last.
Sorry. What about did it work well with the eco-state networks? Like with the radar computing framework?
Okay, so to be fair, that's just something I started like 2-3 weeks ago. So that's extremely preliminary first things, and as you can see, I didn't have time to compare with some naive estimator, which would be okay, take what's on the 7th layer, project it, and if it's not even better to beat this, then there's no fun. I didn't really know what to expect. I was quite surprised to see that the things were that we could predict something, but yeah, a real use of the reservoir would be to go back to the real angle of the original particle in the center and to see if it kept memory of this at the end. This
thank you again. We will now be moving to Mathieu, who will be talking about matrix factorization. He's joining us from Lille. Sound again. Yep. Mathieu, can you hear us? Je sais pas si tu peux nous entendre. Non, vous n'aurez pas. On n'a pas de. Non, la vidéo. Alors, nous on n'a pas. Ah, Mathieu, si tu peux nous. Message. Non. Mais. Pourquoi est-ce que ça marche pas? Non, non, ça va couper. Les dates, ouais. Yep. Non, oui, non. J'ai pas de vidéo, pas de son. Ni vidéo ni son. Ah, on est connecté. Alors, on est bon. Ok. Let's try again. Non, toujours pas. Pourquoi j'ai pas de vidéo ni de son de. J'ai pas de vidéo ni de son de mon côté en fait. Est-ce que tu. Je sais pas si c'est mieux. Non, quitter l'appel. Fuck. Okay. Taking a minute to sort out some technical issues. Ok. Ah, on a du son. Ah, c'est bon. On est bon.
Ok.
On a tout cette fois-ci. Hop, on va mettre en plein écran. Je vais mettre la vidéo de la salle. Voilà.
Hi everybody.
Si tu peux nous partager ton écran et on est.
Ouais, c'est ce que je vais faire de
Et
suite.
on est tout bon.
S'il veut partager. Vous voyez mon écran, c'est bon? C'est aussi Hussein?
Non, on n'a pas l'écran, on n'a que la.
Ah, purée.
On n'a que la vidéo.
Qu'est-ce qu'il fait, Chrome? Bon. I desperately try to share my screen, but it doesn't work. Je coupe la vidéo et on va essayer de voir si ça marche mieux.
Ouais, ok, ouais. On a toujours l'audio, mais pas de. Live debug. Si ça marche pas du tout, sinon tu peux peut-être m'envoyer les slides et je fais passer. Ouais. Et je fais passer les slides à la main.
Ouais.
On va faire ça, on va se coordonner. Tu peux me les envoyer sur mon mail.
Ok.
Je vais les récupérer. Pof.
Ok, c'est parti sur l'adresse LightOn.
Ok, ouais, super, je récupère ça. Hop. Juste temps qu'on se mette à jour. Ok, je les mets sur l'écran. Ok, alors, je mets ça en grand. Hop. Ok. C'est bon alors. Bah, c'est quand tu veux, je ferai passer les slides.
Okay, so thank you very much, Julia, and thank you very much to Igor also for the invitation. I hope you can hear me correctly. So I'm happy to preach. I'm associate professor at ULCO, so it's in northern France. And we started a work recently about weighted matrix factorization with random projections. So actually, my talk will be mainly about weighted non-negative matrix factorization, but the proposed framework can also be applied to matrix factorization without sign constraints. And first, let's say that it's a collaborative work with Farouk Yahya, who is a PhD student with us, and Gilles Damer and Gilles Roussel, who are my colleagues. And the thesis is funded by the Région de France, so that I think. And actually, I will also present some previous work because this work was initialized by previous work with Clément Dorfer about mobile sensor calibration. So I will talk about mobile sensor calibration to explain the motivation behind the work with Farouk. So before starting, let's talk about matrix factorization. So it's actually a classical problem in machine learning or signal and image processing. And we aim to factorize a matrix X as the product between two matrices, A and S, which are, oh, sorry, it's slide number 3, which are in orange for A and blue for S. And on the next slide, it is actually really classical in source separation or source localization. So in source separation, X is the observed data matrix, A is a mixing matrix, and S is named the source matrix. So if we just focus on A, we can perform blind mixture estimation. And if in addition we know the tensor array geometry, we can perform source localization. If on the contrary I only focus on S, I perform source separation. Or if I already estimated A and I know the sensor geometry, I can estimate S using beamforming. A wider family of approaches on the next slide is Lorand matrix approximation. So it can encompass source separation, but also other applications. So in that case, we assume that X is a noisy matrix, possibly with missing entries, but it's low rank. A is a weight matrix, and S is a latent variable matrix. So it can be applied, for example, in topic modeling, like in online news. So in topic modeling, the matrix S is composed of several rows. Each row is dedicated to, let's say, an article, and each column of X is proportion of a specific word or a bag of words. We assume that several articles talking about the same subject will have similar signatures in terms of word and bag of words. And so by factorizing this matrix X, we can provide some kind of clustering, which is, for example, used in a more complicated way by online news readers. An alternative is, well, another problem which is quite related is collaborative filtering. So it has been popularized by Netflix Prize. We have users on the rows of X, and on the columns of X we've got movies, and some users can rank the movies. And of course, no user can see all the movies existing on Earth. And the problem is, how can I provide new movies that the users will appreciate? And so the assumption is to say that the users are some kind of mixtures of some profiles we have to learn. So the profiles are learned in S. A is a weight matrix, and if I'm able to fully estimate A and S, I can fully estimate X, and by this way, I can see which movies a user should like. So it's a way to provide a recommender system, and it has been actually really popularized 10 years ago. A third application is graph analysis. So if you have graphs, you can transform them into a matrix, for example, Laplacian matrix, and then perform NMF, or matrix factorization without a sign constraint, in order to learn some patterns. And if you go back to the graph, then you can find some subgraphs which are interpretable. And this, for example, was applied to bike-sharing system. On the next slide, I'm going to talk about non-negative matrix factorization. So actually, many problems, the matrices X, A, and S are non-negative. For example, in chemical source separation or hyperspectral imagery. And the non-negativity constraint was found to be really useful because it usually gives a better interpretability. So on the picture, you have an example from the seminal work by Li and Sung. So it's a well-known phase dataset. So Li and Sung considered several hundreds of faces. They unfolded all the faces as vectors, and they constitute a matrix, and they applied an NF on it. And okay, the promise transpose with respect to what I was saying, but actually on the left matrix, you have some patterns which are in the A matrix, and the S matrix here is corresponds to weights. And NMF outputs are naturally sparse because of the additive structure of the matrix factorization. So you find sparse and interpretable patterns in the matrix A, while on the next slide, if you compare with no sign constraint like PCA approach, the patterns are distorted faces here. So it's not interpretable as NMF. So red means that it's negative entries, and white to black is positive entries. So that was the basic introduction about NMF, and I'm going now to explain the motivation. So on the next slide. So we were interested in sensor calibration actually for making air pollution maps, and we faced one issue towards calibration. So basically a sensor is transforming a sense phenomenon as an electrical activity like a voltage, and going back from the voltage to the phenomenon is done through calibration. And so for gas sensors, for example, the calibration is quite time-consuming and costly because you go to a controlled chamber, you control the quantity of gas you want to sense, so you know exactly its concentration, you measure the output as a voltage, and if you do that for several concentration, you can make a regression and find the calibration function. The issue is that when you have a lot of sensors, so that's the next slide, like here we have 4 sensors, and if the calibration will be quite costly and it's not always physically possible to perform it. So if we don't perform calibration and if they say the same thing, actually the data will look like my Daltons. I mean, the signals will look the same, but they won't be exactly the same. And a strategy consists in trying to compensate the sensor drift using data themselves. So next slide, I introduce a few assumptions to show how calibration can be seen as a low-rank matrix factorization. So a rendezvous is a classical definition, is temporal and spatial vicinity between 2 sensors. And using this rendezvous, we can define quantities delta D, which is a distance, and delta T, which is a time duration, to create a scene, which is a discretized area. So using this discretized area over this time interval, sensors can share several times in different positions. And 2 sensors are in rendezvous if they share the same cell or the scene. What we proposed was to unfold this information. So on the right part of this slide, you see my observed matrix X. I have the spatial samples along the rows, and I have the different sensors along the columns. And if 2 sensors are in rendezvous, they share a same position in the same row of the data matrix X. On the next slide, actually, we can see that blank calibration is actually a structural matrix factorization problem. So I have on the left my matrix X with all the sense data of all the locations. It can be written as a matrix A, which contains the physical event I want to sense. And on the right part, S contains all the calibration parameters. And I add a matrix W, and O, the O symbol means Adama product. So W is a weight matrix which is equal to 0 if we don't have data, and which is equal to the confidence in the sensors otherwise. I won't go through the detail, but we proposed several approaches for that purpose, and we found it was pretty efficient. So in the next slide, I show some comparisons with state-of-the-art approaches with respect to the missing value. So in red is a state-of-the-art approach, which is a multi-hop calibration technique, and it uses our technique. On the x-axis, you see the missing value proportion, and on the y-axis, you have the root mean square errors in terms of calibration accuracy. So we see that when we don't have a lot of missing entries, we perform similarly to state-of-the-art approaches, but when we have less data, we still perform correctly, while the approach, state-of-the-art approaches are not working that fine. On the left plot, it was a noiseless case, and on the right plot, it's a noisy case. The second good point of this approach is that we can provide a first estimate of the sense phenomenon. And so we had a first approach, which is named INCAL, where we can just recover the known entries. But if we add some sparse assumption on A, we can fully recover the sense phenomenon. So actually, we started from that, and we developed methods based on multiplicative updates, which are known to be extremely slow in NMF. But when we started from scratch, we had to start with something. And the issue is that in this kind of applications, you have, let's say, hundreds of sensors which sense every 30 seconds some phenomena. And so you quickly get a lot of data, and so we had to face this data deluge, and we have been looking for alternatives to multiplicative updates to be faster. So on the next slide, I explain how we could deal with. So I'm on slide number 9. So on the left part, you see the structural approaches which are slow, like multiplicative updates or projective gradients. And if we want to fasten them, we have several options. So distributed computing, like Liu et al., which have been using the MapReduce framework. We can also perform online factorization. For example, Mera et al. Provided that 10 years ago. We could also use a fast solver. So Bon et al., they are using nested gradient descent to accelerate the optimization. And we also have randomized strategy. So several authors, including us, investigated that. So in 2018, we started to look if it was making sense to still use random projections while we are using a fast solver like Nesterov, and we found that even on the small cases, small scale matrices, it was providing some improvement. And so we decided to work on our problem, which is randomized strategies with missing entries. But before introducing that work, I'm going to explain how randomized strategies are working with standard NMF. So we initially want to solve x is approximately equal to A times S. And we can see that we have much more rows in X than we need to update S, and much more columns in X than we need to estimate in A. So the idea is to have a bilateral compression. On one side, I can I can compress my matrix in terms of columns by right multiplying it by a matrix R. So yes, sorry, it's the next slide. And if I do that, I compress X, I compress S, but I don't compress A. So the update of A is still possible. Similarly, if I multiply on the left side by X, by a matrix L, I can fully estimate X, I can compress S, X, I can compress A, but still I have the full matrix S, and so its update is still possible. And this strategy is pretty simple, it's pretty efficient, but we need to find a way to design R and L. And the idea is to use random projections, which are based on the Johnson-Schwarz lemma. So I won't provide detail about this lemma, because I guess you all know them. But in NMF, we face several strategies to compress matrices. And so Zhu et al. In 2012 proposed to use Gaussian random matrices. So I'm slide number 11, sorry. So Gaussian random matrices are based on the proofs of the Johnson-Schwarz lemma. But later, Tepper and Sapiro showed that structure random projections were more suited for NMF than the standard Gaussian matrices. So structure random projection means that we are computing a kind of basis using power iteration, but a randomized power iteration technique. So this approach is pretty efficient in practice, but it's slower, of course, than Gaussian projection. And an alternative to randomized power iteration is a randomized subspace iteration, which is similar in theory to RPIs, but it's less sensitive to random errors in practice. So on the next slide, I'm going to talk about the different ways to solve my problem. So we have the weighted problem which is shown here, and the trick is that most techniques are based on slow solvers. A few use some similar strategies as used in unweighted NMF, like a fast solver, but no existing approach was using random projection to the best of our knowledge. And so we went on the next slide to the different ways to take care about the weight matrix. So we have several strategies. The first one is to take into account the weight matrix W in the gradient optimization. We found in several previous papers that it can be efficient for multiplicative updates or gradient descent, standard gradient descent, but if we use, for example, an estimator of moment, it's not working at all. Another alternative is an expectation maximization strategy. So the idea is in the first step to estimate the unknown entries of X in order to have a complete estimate of it. So that's the equation 1. So I take the known entries of X and I complete it using the best estimate I have, which is the product A times S. And then in the M step, because my matrix is fully complete, I can apply ANMF technique. Last approach is the stochastic gradient, where we update a single variable at a time. But to the best of my knowledge, it was only applied for in the case of binary weights. And so on the next slide, I introduce the idea of our proposed method. So our idea was, because we found that ER strategy was well suited with nested gradient descent, we decided to keep this structure and to try to implement inside the projection. So in the E step, we first complete the mixing matrix, the matrix X, and then we apply a randomized power iteration or randomized subset iteration in order to derive the compression matrices L and R. And we can then define the compressed matrices X, L, and XR. Then in the M step, we iteratively update A and S, using the compressed SR and AL. So there's a main difference between this kind of technique and the standard approach. In the standard approach, you just compute L and R once and it's done. Here, because we re-estimate X in each step, we have to recompute it again, and computing RPI or RSI is quite time-consuming. So actually, the E step in our experiments was found to be 3 times slower with the compression than without. But in each pass of the M step, the CPU time is 10 to 100 times faster, shorter than with the state-of-the-art approaches. So there's a trade-off to find between the time lost due to compression and the number of passes we need to investigate in the M step. So to show the efficiency of the approach, we experimented some simulations. So we ran tests for 60 seconds and we repeat 15 times the following experiment. So we generate random matrices A and S and a full matrix S, X. So X is 10,000 by 10,000 and it's rank 5. We randomly suppress some data to generate the actual matrices X that we are going to process with a varying sampling rate from 10 to 90%. And we compress the matrices using randomized power iterations. We investigated the use of several solvers, like multiplicative updates, projective gradient, alternative least squares, and nested iteration. And we use the 2 performance criteria, which are the relative reconstruction error, the RRE, which is just the quality of estimation of the matrix X, and a source separation criterion, which is similar to interference ratio, where because we don't have a lot of columns, a lot of elements in S, we estimate the columnar part and the orthogonal part of the estimated rows of X with respect to the true ones, and we can derive a similar to interference ratio, which is a kind of similar to loss ratio. And on the next slide, I show some results. So there are a lot of curves, so I will divide them in 2 parts. So again, I will next slide. So I will just first focus on the results obtained with multiplicative updates in orange and projective gradient in blue. On left plots, you have the two results in terms of SIR and RRA with respect to the missing value proportion in the x-axis. And in the plain lines, you have the vanilla approaches, and in dashed lines, you have the randomized approaches. So in the left plot, we only have one pass inside the M step. So as I told you before, the E step is time consuming, and actually with only one pass, we don't have enough time to compensate this lost time in terms of computations. So that's why, in that case, on the left plot, the vanilla approaches are outperforming the randomized techniques. Now, if I'm focusing on the right part of the plots, we can see that, okay, the multiplicative updates are not really efficient, and so there's not a big improvement due to the random projections, but the projected gradient, now we have a significant gain in terms of performance, because we've got again a factor between 10 and 10 power 4, depending on the missing value proportion. In terms of SIR, the results are not that convincing, because actually in source separation, the standard NMF techniques do not guarantee a unique solution, and that's why we can have some local minima, and I think that's what happens in terms of SIR on the left, on the bottom plot and the right part. If now we focus on ALS and NENMF, so the next slide, things are slightly different. So ALS is basically alternating mixed squares, and I just project to zero all the negative entries, and the Nesterov NMF is using the Nesterov gradient to perform the factorization. So again, if I just have one pass per M step, the randomized technique does not provide any improvement, but now if I go on the right part with 50 passes, I have a significant improvement in terms of performance in both RREs and SIRs. So this shows that actually, if I can, and last point is that the performance even of the vanilla approaches was already good, and it's even better. So this shows the relevance and the efficiency of the proposed method. And we tried to investigate more tests that I will quickly summarize in the next slides. So first of all, we faced some stability issues with ALS, because as we are zeroing negative entries along the iteration, it happened in several tests that the wall matrices A and S became equal to 0, so that we had not a number of errors. So we decided to stop using it in the remainder of our test. We tried other solvers like ActiveSet, which is a non-negative least square strategy. We kept the Nesterov method, and we also used their extrapolated extensions. So extrapolation has been proposed recently in NMF by Hank and Gillis, and it's a generalization of the Nesterov strategy. And we found some consistent results with those which are already presented. We then also investigated the NMF performance with Gaussian compression. And so I show some graphics with Nesterov methods. So I have a mu, which is a small oversampling coefficient. So I know that my matrices are rank P, and in my test P are 5. But instead of compressing to P, I compress to P plus mu. And I can use this mu to get more or less compression. So when my matrices are highly compressed, and actually that was a choice by Tepa and Sapiro in the original work on compressed LMF, the performance, which is here shown in black, is extremely bad. So I have in black the median value, and the gray area is the envelope of the results I got on the similar experiment as before. In blue, I have the vanilla approaches, and so I see that the vanilla approach is much better than the compressed method when mu is equal to 10. And actually, this kind of result is obtained with all specific methods. But if I increase mu, of course, I will reduce the error due to the compression, and I can provide some similar performance to the vanilla. So depending the method and depending the test, sometimes the compressed method, so this is the one in red, is slightly better than the blue one, and for other solvers, that's the control. We also investigated more deeply what the behavior of RPIs and RSI, so randomized power and randomized subspace iterations. So we found that on average they perform similarly in our test. So this is the right part. But in this test, we found that RPI had a narrower envelope, which is a bit surprising because our RSI is supposed to be less sensitive to random errors. But up to now, we didn't test simulations with noise, and probably the results will be different in these new simulations. We plan to perform these analysis next week. So, as I said before, to conclude, this work is pretty new for us, so I just have practical results, but we've still introduced a new framework to combine random projections with a weighted matrix factorization. It's based on an EM scheme, so expectation maximization scheme, and it outperforms non-randomized techniques under some mid condition. We need to have enough passes inside the M step to compensate the lost time in the E step. Currently, the bottleneck is the time to compute the compression matrices at each E step. So RPI is pretty slow, RSI as well, and we plan to try OPU provided by LightOn in order to see the gain we can have. But I'm afraid it might not be that efficient because I don't think the bottleneck is really due to the Gaussian projection term. It's more due to the X transpose X power Q computation, and we are actually working on refining the compression strategies using only Gaussian compression, and we have some first results which are really good, but we try now to better explain them before showing them. If they work correctly for much more tests than what we already have, we plan to implement them in OPU to see the improvement. In terms of future work, we also aim to extend the proposed strategy for informed and structured LMF techniques that we will apply to mobile sensor calibration. So the next slide, I just propose you some links for some of our codes. So feel free to read our papers and try our codes. And if you want to go to the northern coast, you will be invited to present your work in our laboratory with a great pleasure. Thank you very much.
Thank you, Mathieu. So we will move to questions, and I will be relaying to you the question from the audience. Let's go. Does anyone have any question? No, not at all. No takers for questions.
Pourquoi est-ce que les projections aléatoires ne sont pas un bottleneck? Je n'ai toujours pas compris ça.
So in order to be sure, your question was why Gaussian compression is not working correctly, right?
No. Why are random projections not a bottleneck for you?
Okay, it's a bottleneck in terms of, it is a bottleneck because of course you have a lot of computations and this takes some time. There already exist alternatives like GAN-COS, so a mixture of count sketch and Gaussian projection to mimic the Gaussian projection efficiency and it's less costly. I'm thinking that it won't be a big bottleneck using only Gaussian compression. Because from what I saw from optical process units, the specific computation of the Gaussian compression, so just multiplying my matrix by a Gaussian compression matrix, purely random matrix, can be efficiently done with your DMD and the optical process unit. Okay, it's an assumption because we didn't try it yet, but if it works as I'm expecting, this should not be a big issue. But on the contrary, the big issue is currently in the RPI because still the X times X power Q takes a lot of time to compute. And this, it's an iterative process, but I don't think it will be as fast as just using random matrices using a physical system.
Okay, thank you.
Any more questions? No? Okay. Well, thank you a lot, Mathieu.
Thank you very much, everyone.
Thank you. and bye. So we are done for today. Thank you for attending. If you want to continue the discussion a bit, we can have a beer on our rooftop above with a very nice view of Paris, or not so nice depending on the weather. And that's it. Thank you for a lot for attending, and see you for the next edition, which will be on the 2nd of April 2020. That's it.